of topics, which includes quantum algorithms for NISQ devices and beyond. He will handle today's session jointly with Mr. Shantan Pramanik. Shantan has completed his graduation in electronics engineering in 2019 and has been working in TCS research in the field of computer vision and quantum computing. He has authored 4 research papers in internationally acclaimed journals, and he has 1 patent filed. He's also a Qiskit advocate and has hands-on experience on Qiskit, Amazon Bracket SDK, and Penilyn. Today, Dr. Chandra and Mr. Pramanik will talk about their exploration in quantum algorithms and NISQ systems and beyond. We will start now. If you have any questions, please type them in the chat box. We'll address them once the talk ends. So over to Dr. Chandra and Mr. Pramanik.
Dr. Chandra, welcome.
Yeah, thanks, Professor, for the invitation, and thanks, Rhea, for the nice introduction. Sayantan, we can just start with a small 1-minute video about TCS research. And after that, I think I'll just start my portion of the presentation.
Sure, sir. I hope my screen is visible now. I'll mute myself and play the video, but I don't think audio has been working. So I'm very sorry about that.
Hope that's all the video, I think, for the time being. So there is a web page on TCS Research also. You can get more details, including various research groups and the activities which are happening, including the key publications and patents and so on. And of course, so you must have noticed, actually, we have diverse areas, actually, in terms of research and innovation activities. So feel free to just visit our website and then get more details. Of course, towards the end of the session, if the time permits, if there are any queries, we will be happy to answer as well. So let me just start sharing my screen. Is it visible?
Yes.
Yeah, it is visible.
Yeah. Let me just also know whether my mouse movements can also be just deciphered. Okay.
Yeah.
Okay, thanks a lot. And again, good evening, everyone. So we will be just spelling out few initial explorations we have carried out in quantum algorithms. And of course, in order to just put the context, let us just start with some kind of acknowledgements, basically, because we have also started learning this area rigorously from last 2 years. And also some of the material I've used in these slides, actually from the slides of Professor Stephen Garvin and also Professor Roman. I think their affiliations are already there. I think most of you may be knowing those people. And they've generously just shared their slides. And also, we went through many courses and lectures, which actually definitely influenced our journey in learning from last 2 years. So we have to just express our deep gratitude to all the intellectuals involved. Because of them, actually, we learned and just carried out some small things in this beautiful area. But there are too many to list. But we cannot miss one gem course which really just motivated us, actually, that is Quantum Machine Learning by Dr. Peter Wittek in 2019. That was one of the kind of springboards, actually, for us, actually, to just move forward. And also, so far, in the last less than 2 years, we have already handled 8 interns and 4 from ISET Calcutta itself. That is actually a good thing to just speak in this platform at the forum. And of course, needless to say, we all grew together, actually. Let me just actually go to the quick recap of few facts. Of course, now actually we are almost towards the end of the summer school. When I just tracked actually the various schedules and the dates and all those stuff. So we must have already been familiar with the various aspects in terms of quantum computing, qubits, and so on. But just to put a perspective from an applied scientist way, I'm going to just capture a few important points now in the next 1 or 2 slides. So if there are duplications, or if you already know, please bear with me actually. But sometimes you may get a different perspective as well. And also, you may just get a sort of kind of an idea when people just want to just put more focus on implementations or getting the things delivered as solutions. What are the key points usually they take away from the existing literature or the knowledge base? That also perhaps I think one of the things to just we are planning to just convey in this session because we are from industry. So I think you must have noticed already the title. It is about quantum algorithms for NISQ and beyond. So we will just clarify those terms actually, I think very soon. So, but when you say quantum algorithm, actually, definitely, you know, we are telling that I think those algorithms run in quantum computers. So quantum computers actually use qubits. I think you are all just actually very familiar by this time. And I want to just bring 3 important aspects in this quantum computing. One is the superposition, entanglement, and interference, basically, because these are the 3 important ingredients actually, which actually enter into even the quantum algorithms or any quantum computing per se. So I think we know qubits, basically it is a kind of an entity with 2 distinguishable states. But one thing is actually compared to classical bits, they actually just can simultaneously just have the aspects of both 0 and 1. So therefore, I think this is, I think, well-known superposition concept. Here itself, we can just make out that I think the uncertainty is a feature actually here because it is actually having aspects of both 0 and 1. And the familiar representation is the Bloch sphere. And of course, a qubit state can just lie on this sphere anywhere actually. So when we just measure, actually, then there is always a kind of result which we call collapse. Basically, those are all familiar concepts too. So measurement results will always give 0 or 1. So just one important point actually, which is to be just understood here is when you say it can lie on anywhere in the Bloch sphere. So it is actually it's a continuous or the analog of quantum states are the encodings. But when we measure, we will get a kind of discreteness actually. So in order to reconcile this, actually the neat way to just put the things in place is through randomness. So what I'm trying to say is randomness is inherent to this quantum computing or any quantum mechanical phenomenon. So that's what actually I'm trying to just bring out. And this figure I will just again revisit. This actually gives a fantastic picture of how the quantum algorithms actually have to be just visualized, at least from a kind of an implementation person's perspective, basically. And this figure is I've taken from Professor William D. Oliver's slides from 2019. So I will just explain that actually in next 1 or 2 minutes. So now, I already just talked about qubit superposition, and now actually, whenever we say quantum computing, basically even in classical computing, we just start with classical bits and then move to registers. That means a kind of sequence of bits actually. Similarly, this is not a kind of new thing. Even in quantum computing, we just go to quantum registers where we have a series of n qubits basically. One good thing about this quantum stuff is basically the concept of entanglement. So it can be seen in the sense of a global phenomenon. I'm not going to just go into details of this. Basically, what it means is in the register, if you have n qubits, if they're entangled, then if you just actually carry out some kind of an operation on one, it will have an effect on others, basically. So that's actually a very important and powerful concept. And that is very much essential, basically. And now we have just talked about superposition and entanglement. And both the things actually are very much essential, particularly when you just say superposition in the context of a quantum register. We have basically a state composed of 2 to the power of n components or aspects. I think these things are all well known. Of course, now when you have more qubits, I think we have 2 to the power of n aspects of the components enter into our state superposition. I mean, the bigger state has got these many components are the aspects. And of course, now they're getting added together. Of course, there would be some kind of complex coefficients in between. Whenever things are added together with some kind of complex coefficient in front of them, that we can immediately see there is some kind of an interference happening. So somehow we just managed to, at least in the hand waving manner, able to just bring the notion of superposition, entanglement, and also the interference. And we will see how actually they just facilitate the algorithm execution. That algorithm action we will just see in a moment. So this is very useful. And also I think you must have already noted, because of this 2 to the power of n, the state space we just talk of is very huge. For example, when you just talk of 53 qubits machine, which we just always just mention and see in the literature and the newspaper and so on. So we have actually these many number of states. It's 9 into 10 to the power of 15. So that means basically when you just do an operation on this register, at least in an ideal sense, it means that it is actually we are doing an operation on this many dimensions in one time, basically. So that is actually a very important notion to just keep in mind. And of course, it's very well known. And the other thing is basically when we just actually think of quantum computing or quantum algorithms, and many a times we just talk of exponential speed up. And many a times we just miss this entanglement also in many of the introductory courses, but it has to be just noted that this exponential speed up actually emerges because of the exploitation of the entanglement. So there is a nice paper by Richard Jozza and also Linden actually in 2003, so that you can refer. And also there is this beautiful argument which we can just obtain by how actually we have to transfer the Hilbert space, because we are saying some Hilbert space or the state space actually, which is a very higher dimension. When that state space or the dimension, higher dimension is available, basically we have to exploit the power of that entire Hilbert space. That also just suggests that actually we have to just kind of encache the power of entanglement. Again, I will leave it as an exercise for the students to just actually work out why. The answer is also in Belak's beautiful book on quantum information. So let me just actually go back to this quantum algorithms, and then we will just see how actually things are just happening in terms of the visualization. So when you just say, let me just again, before going to that, I think this is a very useful sort of a slide to just keep in mind. I have gone through this video so many times, perhaps I might have memorized it actually. I think it's one of the very influential sort of slides actually, and the portion of the video from Professor Oliver. So I think when you just say algorithm, basically, I think let us now stick to gate model based quantum computing. Of course, here, at least for this kind of, for this lecture or this session, we will be focusing on two flavors. One is the quantum annealing, which is a kind of an approximate version of adiabatic quantum computing, and the gate model based stuff. So when we just restrict ourselves to gate model based computing for the time being, you know, when we say classical computers, we apply gates basically, and a NAND gate is universal gate. Of course, we just see and a NOT gate. Basically, with those two gates, we can perform any Boolean logic, classical Boolean logic, I'm telling. So of course, Boolean logic is classical. So then similarly, we can just carry out any quantum logic with a handful of 1 and 2 qubit gates, basically. So that's why when we just go back to the diagram on the algorithm action, we will just start with some kind of one single qubit operations and also coupled qubit operations, or the two qubit operations. Now, I think we have already just considered a register. So there are various aspects of the components. The state is a superposition state with various components. And now we just apply a single qubit operation, let us say. Even if you just apply it for 1 qubit, because of the entanglement, I think it just actually just affects all the sort of other aspects of the components of the state. So that's the beauty of it. And actually, once they do, I think then there is what is called as quantum interference effects, which actually just manifest and which actually change the sort of coefficients I was mentioning, complex coefficients. So that is actually results in this. And then we apply just, let us say, coupled qubit operations at the 2 qubit gates. There, when you say coupled QA, the 2-qubit operations, depending upon 1-qubit state, we just try to put an operation on the other qubit, basically. This also actually results in a kind of, when they are entangled, actually a kind of effect on all the aspects. And then further interference, again, just actually results in this, again, the alteration of the modifications of the coefficients, alpha prime, beta prime, etc. They move. This is actually an algorithmic flow, basically, in the gate circuit model of the computation. So now, if you just and of course, there is a very sort of nasty problem that I think I don't have time to just touch the measurement aspects, but it is very important, basically. So when we just measure, actually, this is a very key concept. When we make measurements, we have an exponential slowdown. Of course, we had the exponential blow up in the states. Means we handled together because of that massive parallelism emerged. But only thing is, when we just measure, we just actually slow down. Therefore, actually, we have to make sure that as algorithm designer, an appropriate coefficient to just have a very significant value, much close to 1 means, of course, this whatever the state, for example, 001 here, emerges as the right answer to our problem. So I think that's actually how an algorithm is going to work. It is a kind of not a completely physical or not mathematical, a kind of fantastic visualization to be kept in mind when we just start implementing or just having a feel for these kinds of sort of aspects or the concepts, basically. So this is about the quantum algorithms. And so our job is, this is actually the rule of, whatever the algorithm designers kind of a goal, basically. So that's what actually I've just tried to cover. So now I'll just quickly just spend about 1 or 2 minutes here. So I think when we say massive parallelism, already we have just seen the 2 to the power of n kind of stuff. So this leads to performing certain computations that are impossible on any conventional computer. So this actually has to be just has to be kept in mind. And also there is one more factor. I think whenever actually, particularly beginners like us, when we enter, always just we are getting boggled down by this. This is not because of clock speed, but rather the complexity of the task scale differently with the problem size n. So for example, if a classical algorithm just takes e to the power of an exponential kind of steps in the problem size n, then actually a quantum algorithm, if it takes the polynomial one, then the time can also be just proportional to this actually. Of course, there can be a very nasty constant. I'm just leaving this. So what I'm trying to just say is certain problems, certain classes of problems can be very easy for quantum computing. So this is what actually this beautiful diagram actually is again capturing. And one more thing actually, which is very important to just note is there are, I think I will just come back to heuristics a little later, but for the time being, I think I will just stop here because there is also a backup slide to just quantify in a much more rigorous way this complexity stuff. Since we are from I'm not from a computing background, but since ours is an IT industry, so these complexities and other things are really of interest to us. And so therefore I have captured some more information in the backup slide. If some discussions are just provoked actually towards the end, we will just come back to it a little later. So the one thing is basically we have to just choose the right problems which are actually can be comfortably solved or can be neatly handled by quantum computers, basically. So now I think this is actually very, I'm not going into the details because I think there were a lot of talks and sessions I had seen actually in terms of the various problems with the present computers. So I'm not going to just elaborate on this. So we have the decoherence, which simply means that the qubit is actually going to last for only a short duration. And we have the gate fidelity because always the operations are a little, means of course erroneous. Why? I think there is a fundamental kind of notion also which is there. And again, if there is a question, I will just address towards the end. And then actually, of course, we have the readout error. And also the present computers we have actually just got in the various industries. Actually, they have got the connectivity problem also. That means all qubits are not connected to, each qubit is not connected to each and every other one. So these actually just results in some kind of a noisy situation. And we just refer to this scenario as noisy intermediate scale quantum technology. And of course, we are seeing in the range of 50 to 100 qubits. Of course, there is a roadmap to just go up to 1,000 by IBM in next maybe 2-3 years. If I'm not correctly, just if I'm not mistaken, actually. So then, so our goal in the NISQ kind of era is basically, can we do some meaningful quantum computing? And also we have to just use the limited number of operations in the algorithms. And also while doing that, actually, if there is some kind of proof that there is a quantum supremacy which can be brought out, there's actually a kind of neat goal for any NISQ era, basically, or the NISQ era researchers. So let us just go a little bit further. So this actually, again, just captures very pictorially, basically, because there is a beautiful kind of I think it is not a very rigorous stuff. There is what is called as width and depth of a quantum circuit, basically. And this product also should be, I think, that's to satisfy this error rate. When I said NISQ devices or the NISQ computers have error, there is an error rate, obviously. So I think we have to just make sure that I think this inequality just gets satisfied. And of course, this WD should be much, much lesser than 1/epsilon. So, and what it means is, at present, we can only run some shallow quantum algorithms. Okay, but only thing is, more qubits we use, then only, otherwise I think we can just definitely just with fewer qubits, even if you go for a slightly deeper circuit that can be comfortably simulated or efficiently simulated through classical means. So that's not the way, basically. So we want to just go for a larger number of qubits as possible. And also just, I think that present limitations actually allow us only for good to just go for a shallower circuits. But the only thing is, I think many of the dual algorithms actually just require very large depth circuits that actually we will just touch upon a little later when Sayanthan just talks about amplitude amplification. So let us just now, I think just this is a quick kind of a summary actually of the basic facts. Now, I just actually go to a little bit of explorations. Only few things we will be just covering. And the rest of the things, actually, I think you can always just contact us for more details about the papers or otherwise. So we started actually a collaboration with TIFR. And of course, TIFR has got the INDIC computing, quantum computer basically getting built. And TCS was actually trying to just collaborate for providing what is called as TCS India Cloud. And also when this collaboration was happening, there was some interest in just using the D-Wave annealer. And some experimentation was carried out with actual hardware by considering small-sized optimization problems. One example is an assignment problem. I think I'll just leave it to the students to just find out what is an assignment problem from Wikipedia. So when we say the annealer, I think already you must have just heard of adiabatic quantum computation. This is a kind of non-ideal implementation of adiabatic quantum computation. So here actually the two important things to note is basically the problem Hamiltonian and also the mixing Hamiltonian basically. So, and when we say optimization problem, basically definitely I think there is a cost function basically that are utility function, if you want to just call it in a more generic way. That cost function has to be minimized. And this, whatever the problem Hamiltonian just captures that cost function actually. So let me just actually just without going into too many details, so once this mixing Hamiltonian and the cost Hamiltonian are put in place, what we are actually just looking into is, of course, I just mentioned that I think the cost function is getting just captured by this problem Hamiltonian. So basically, we are just seeking a kind of a ground state of the system, basically, where actually this is a kind of an Hamiltonian. And if you just get a state which corresponds to the ground state, then we are actually getting a minimization kind of a state, or we are just minimizing our optimization problem. If you just see this figure, actually this is an output, actually some 001 has come. So because again, there are two more things. One is actually those who are already comfortable, they can just see it as an Ising model. And also there are some kind of, when you say Ising model, there is also kind of products which are involved. Why this is important, I will just immediately spell out in the next slide. So this is actually a kind of things to keep in mind. I also have one small question you can note down, then you can answer later. So this annealer is not a universal quantum computing paradigm. So just just suggest how to just make it universal. So now let me just actually, so basically what we are trying to do is we are just formulating the optimization problem in terms of a particular Hamiltonian, and then actually trying to just get the ground state. And once we just get, I think we have the answers. So basically it's also just suggesting that we are actually just trying to just get a kind of a string of binary variables as the answer. That means ones and zeros. So we are actually just making a case for binary optimization here. And also, when we just saw those Ising Hamiltonian, we had the quadratic terms actually. So immediately we can just see that actually these kinds of architectures are neatly going to just handle what are called as quadratic unconstrained binary optimization problems, or the QAoa problems, which are very, very important optimization problems. I will just again leave it as an exercise to just find out about 20 plus different problems can be mapped into this QAoa. So they are, of course, basically very hard problems. And therefore, people are looking for very good QAoa solvers and fast architectures, basically. So this actually just sets the context for QAoa. And in our initial explorations, what we just did was actually to just focus on max cut, which is a QAoa problem. So what is that max cut? I think, again, there is no need to just elaborate. Given a graph, basically, I have to just somehow just put the nodes into two baskets in such a way that the number of edges actually which are connecting dissimilar nodes, which are in the different baskets, have to be maximum. This I'm just telling when actually the edge weights are equal. When there is an edge weights are also to be considered, then actually we can just even maximize the weight of the number of edges, maximize the weight of the edges which are connecting those two dissimilar baskets. So this is actually about the max cut. And why we just started actually, again, I think I mentioned about QML course. And this problem, even though I just started about a graph problem, it neatly maps into one of the most primitive sort of tasks actually in any machine learning. We start with some kind of clustering. So here actually we are doing a binary clustering. That means we want to just put the data points into two baskets. And actually, so once the data sets is given, we can just define a distance or similarity measure between two data points. And then actually we can just formulate a matrix by considering distance between every possible pair. And this matrix can be treated as an adjacency matrix, and then the graph can be just considered. Then we have each vertex and also the edge weight corresponding to the distance. Now the clustering can be just formulated as a max cut problem. Even though we just started to enter into QML through clustering, we somehow just actually just landed in again the optimization problem, which was also just earlier explored in our research group. So that is actually a very good thing. And now, even though I'm just talking about this, whatever the graph and then the clustering and all those things, I always suggest youngsters to just go through some of the blogs, because some of the blogs are really extremely useful and provide great insights. So you may just get still actually a little bit blocked actually in terms of the max concept and also just clustering and all those things. And there's a beautiful sort of blog I think I've just already listed here. So you can just go through it. For example, if the student, I think once, I think there are two stories. One, I think in one is about a teacher and the class, basically where students students used to exchange the notes, and the teacher somehow wanted to just minimize actually the exchange of notes by putting a partition and also just grouping the students. So then how do we just do that? Of course, this was the initial kind of exchanges which was happening. Then if we just put that as a max cut problem, basically, then we can just actually reduce the number of exchanges to only 3 instead of 22, basically. That means if you just put this green into one side and then there is a big kind of a gap, and then all the blues are sitting there. So then actually, if you just see this graph, I think this falls neatly into the max cut problem. Similarly, there is actually the same problem can be just looked into a kind of merchants problem that I will just leave it as such because in the interest of time. And also, I think, again, a reiteration, already I just mentioned Ising model, just knowing it, just taking for granted that I think you've already seen these kinds of models in your courses or other earlier lectures. So max cut, like any other QAoa, maps into Ising model. So I wanted to just actually bring that again. And you can just go through our archive paper for actually just get more details about the notations as well as actually how things are actually getting worked out. So, of course, still I'm in the classical domain. So that means I'm just trying to seeing it as a classicalizing Hamiltonian function and trying to minimize basically. Then then enters the quantum basically. So how do we just again go through the quantum steps to just solve these problems? So it's very actually easy. Of course, the recipe is easy. Actually, the relevant mathematical aspects and other things may just even involve a lot of Hamiltonian dynamics. So we had those kind of spin variables. When you say Ising model, basically when I say SI, those are all spin variables basically. That means I'm just trying to formulate the optimization problem in terms of spin variables. If you just replace all these SIs by Poly-Z operator, that's kind of Dirac's recipe. Then actually we have the quantum mechanical formulation. We just translated this classical Hamiltonian function into the quantum mechanical Hamiltonian operator. And now, once we have the quantum mechanical Hamiltonian operator acting on our system, of course, we have that is actually influencing our system. Then we seek the ground state of the system, which is getting governed through that Hamiltonian. Once we just get the ground state, I think we have the solution basically. And that for that, we can use either the D-wave machine or basically the gate model quantum computing through quantum approximate optimization algorithm. QAOA I will just touch upon a little later. So now you just see why we just keep seeing this remark. Quantum computers are better matched processors for solving QAOA problems. It naturally fits into just solving these QAOA problems. And then again, still there is a gap that we will just clarify a little later when we just take up the notebook. But just let us say we take a very simplistic case, Hamiltonian, now it's a quantum mechanical Hamiltonian. So this is how it is labeled basically. And now we are seeing, and when you have this Hamiltonian, -3 is the lowest energy. And this system, actually the qubit system, which is actually just under the influence of this, are getting governed by this Hamiltonian, will settle for this 1-0. So this is the sort of solution for us actually. So, but even though it looks a bit simpler, constructing Hamiltonian for a given optimization problem may require careful considerations. So, and we have already worked out in a few problems, including some sophisticated problem related to Airbus computation. But we will just showcase some small thing actually as a kind of tutorial today. So then let me just check my time, 33. Shreya, if we just cross about 5-10 minutes after 7, is that okay, basically? Depending upon that, I will just plan.
Because the next talk is from 7:30.
So we can have time, is it? Okay, thanks for that actually, because we will try to just do some good justice to this session. So let me just now then I think comfortably move. So then we talked about QAOA basically. One of the sort of extensions we thought of course, we were also just beginners at that time. And now also I think we have to admit that basically in this fantastic and very vast area. So we wanted to just carry out a quantum mechanical version of quadratic unconstrained D-array optimization. If you recollect, I think the spin variables and all other things were binary variables. We were looking for a string which actually just was actually taking either the value 0 or 1. That was emerging as a solution basically. Now, what happens now? Let us just again jump back into our clustering. Somehow with that, we just clustered our data points into 2 baskets, or the 2 groups, basically. What if we want to just put into 3 groups? Then we have max 3 cut in the maths literature. Can we just then solve a problem, which is actually quantum mechanically, to just get these 3 clusters actually? Similarly, can we just generalize to D clusters? And that we are calling it as QAOA problem, quadratic unconstrained D-array optimization problem. And of course, again, those who are very careful, actually, they might have just noticed that the important thing, actually, I stress this Hamiltonian, basically. We have to design an appropriate Hamiltonian, basically, to just put the things in place. So similarly, when we just go for 3 class or more than 3 class kind of grouping, or the cuts basically, we have to design appropriate matrices. For example, in the usual Dirac recipe, what we did, actually, we just replaced the spin variables by our Poly operators or the Poly-Z operators. But we have to similarly just replace this SY with appropriate matrices, basically 3 by 3 matrices and also D by D matrices in the general QAOA case. And then we formulated that Hamiltonian, worked out the theory, and also numerical simulations actually we carried out. and obtained the results to just corroborate that whatever the conceptual sort of underpinnings or the conceptual sort of proposals, I can just say. So then, so the good thing is in future, if there are qtrit and qdits are available, these problems can be efficiently solved. And also there is a new qdit-based QAOA kind of circuit, which was just suggested in the paper. So please have a look at it, basically. Otherwise, it would be too much of a detail into only one territory. So that I think is not the intention of today's presentation, basically. So then let us just move a little more further and bring some more areas. So something we told about optimization. When we were just actually just trying to just work on the quantum algorithms, and already I think we were lucky because we were at the right time, right at the exciting time, and also the right problems for quantum computing were already suggested by the community, like in optimization, in machine learning, and in probabilistic graphical inferences. So the problems which are generally hard for some classical computations basically are just getting explored in the quantum community, basically. So in that way, I think we also started looking into sampling because inherently the quantum computing or the quantum architecture is basically random, and that we can just use it for sampling. So sampling Boltzmann distribution is actually very, very important because it is related to inference and Markov networks, basically. So that notion, anyway, it is not our own, because of course it actually just originated from many other people. And we just actually created a couple of simpler examples and ran and then experimented with that. And a detailed tutorial kind of a paper actually appeared, I think, again in 2019, I guess. And again, 2 interns from ICER Calcutta were involved, actually. So they are the first authors for this paper. So, and then we just continued with more explorations on QML and optimization. And then actually, these were all just getting worked out in a kind of part-time mode. And in 2020 October, we just actually just kickstarted the new research in terms of new and enhanced algorithms for NISQ and Beyond. So why that is important for an industry? New algorithms make the biggest computational leaps. So this is the point actually, which is floating around all the industries and the quantum community. Competitive advantage come from the in-house algorithms and IPs. So this is actually, there is no need to explain these kinds of points. Actually, this is self-evident or self-explanatory, basically. So, and also, we are now also, and even we were considering always the gate model as well as the D-wave annuler. Both the things actually we are considering for our problems or the solutions, basically, and also the proof of concepts, which I'm just coming now. So, there is a good research activity happening in quantum chemistry as well in TCS research, but I'm not part of it actually. But of course, we regularly participate in the discussions, but I'm not covering any of those things today. And one more thing we are interested is quantum-inspired algorithms. So because these are classical algorithms, basically. And there is one quantum-inspired algorithm, again, it's available in our QDO paper, where actually just by starting with the degeneracy notion of quantum mechanics, we just arrived at a classical algorithm. So of course, there are plenty of instances of this classical algorithms, which are called as quantum-inspired algorithms, which exist. And that's also good because what cannot be taught in the usual classical lens can be just really obtained through these kinds of quantum inspirations, and they're classical. And also now what we are doing is from initial explorations, we are just consolidating a lot of use cases. We are not listing them, but already that consolidation has happened, and Sayantan has got a huge number of Excel sheets, basically of various use cases actually, which are of interest to our various business units. Because if we have highly diverse business units similar to our research, and we have use cases from banking and finance, life sciences, material design, travel and hospitality related problems, retail, telecom, manufacturing, energy. So all the use cases are getting captured. And now we are moving towards proof of principle or proof of concepts development, basically. And one more thing which is actually to be just noted here is we have a strong presence in cutting edge end-to-end classical solutions. I think we have in all these verticals we call, we have almost end-to-end solutions providers actually for many big clients. So, and also we have exclusive data sets available to us actually, particularly if you want to do quantum machine learning. I think that is one of the plus points with us actually. So, and also I just mentioned about NISQ and Beyond. Beyond means basically, of course, you must have already guessed. So it is for fault-tolerant futuristic quantum computing, which uses error correction. So just as a kind of side note I put. So then why I just stressed about this classical? because the very important thing actually which is going to happen is this quantum classical hybrid will always stay. So that is actually the kind of projection or a kind of thing which is very, very clear in the quantum community. So for example, presently in the NISQ era, we may have very small portion of quantum computing and a large portion of basically the classical computing. And when time progresses, basically then quantum computing may have just a significant portion of its computational load. And even it may exceed even basically the classical one. So therefore, if you just see the present kind of a literature or even a kind of various blogs and even the newspaper articles, whatever you want to just refer, we just keep hearing the term called as quantum accelerators, basically. That means basically we have a classical computing, and wherever some speed up is required, if that can be mapped into quantum, if that can be mapped properly into quantum, then we can just use it as an accelerator. So that's actually the notion, and that we are actually always be just talking. And then just to put the things in place, in this NISQ era, when I said classical and quantum, this hybrid variational approach has become the norm. That means basically we have a quantum portion or the quantum circuit, which is parameterized. And there is a classical computing which actually does optimization and then push some kind of updates actually to the quantum back again. So yeah, of course, this already there was a session on variational algorithms by Sai, I guess. So I think I'm not going to just elaborate these things. So, and also why this is very advantageous, because it's flexible actually. So you can read this. And also one more thing is, once you have the classical thing, the intermittent data can be stored basically. And that can be just cloned as many times we require and then use it later. That's also very important. And also the entire trend, not only in machine learning, but even in optimization and other tasks, is to have various computational nodes. Quantum node, quantum computing node, classical computing node, and again, it may be connected to another classical computing and quantum computing node and so on. So there are various portions which can be just actually just put together to solve a bigger problem. And so this is actually, the compatibility is also just very elegant. Therefore, keeping all these reasons in mind, we will be having this beautiful kind of synergy between quantum and classical to just continue in our quantum computing era. Quantum computing arena, basically. So, and just to give one more example, even I might be talking many things, or the figures may be referring to machine learning. Even if you just go for a combinatorial optimization problem with complex constraints, we have to initially split that into basically QAoa and classical. That's what actually this task partitioning is actually it's referred here. So we have to just right from the beginning, we can't just simply just push something to quantum and classical. They're also very sort of a clever ideation is required, basically to just partition the problem into QAoa and classical. QAoa means basically for the quantum and the classical. So this is a very, very important regime. And this is very useful for solution providers like TCS, because we already have end-to-end solutions, very strong presence in the classical. So then actually identify the right portions which can just go into quantum accelerator. So this is actually the one thing. When I just talked about variational stuff, I can't miss out two very important circuits. I think these are all well known. I think they might have already been covered. One is the quantum approximate optimization algorithm, and another one is variational quantum eigensolver. So when you say quantum approximate optimization algorithm, of course, it is actually just, it's an adiabatic evaluation actually and it is discretized into optimized steps. I'm not going into the details basically. So, but again, if you recollect your mixing Hamiltonian or the initial Hamiltonian and the problem Hamiltonian, this is how the circuitry looks like. Of course, we are moving, we just talked about adiabatic computing, its approximation through annealing. Now, this discretized version, which is leading to gate model, actually just looks like this, basically. And remember, each of these blocks are basically unitary operations. And when it comes to quantum circuitry or the gate model-based implementations, we have to just decompose them into circuitry. So this is, of course, because of this decomposition, sometimes we may just lead into greater depth circuit, which is larger depth. So that's what it may be it is definitely problematic in the NISQ era. So, and of course, this is defined entirely from the problem. That means the entanglement structure actually actually follows from the problem. But let us say if you just start with your own answers at the initial circuitry or the circuit structure, which is parameterized, and then you just carry out the optimization, then we have a variational quantum eigensolver. So therefore, actually, this may be very easy to control in terms of implementation. But actually, this may not be just giving the right entanglement or defining the right thing to right cost function, for example, in the optimization. But I think, again, those things can be tweaked. And both of them are heuristics. I think when I was mentioning about complexity classes, there was a bottom sentence saying that now we have to just look into, in the quantum computing science, many heuristic algorithms which are actually already dominating, already the classical computing is dominated by various heuristic algorithms to solve the hard problems. Similarly, we have to come out with heuristics to solve quantum algorithms, come out with algorithms which are heuristics and which can solve the problems on quantum computing. These two are basically the heuristics, actually. So this is actually, I want to just mention. Why I'm just stressing this is, when you just talk about NISQ algorithms for NISQ, there's plenty of scope to come out with this heuristics. I'm not going to define what is heuristics. Please take Wikipedia. Basically, I think what it means actually rigorously as well as in a kind of literal sense. So then I'll just take 5 more minutes and then just stop it. So I think again, the variation principle, I just put a sort of a box at some kind of sentences to just for mathematically inclined people, because when people talk of variation principle, they always try to link the calculus of variations. How this is linked, that is captured here. Of course, these are all existing in somewhere, but I'm not recollecting the resource, but these are all useful to just read. Now, our present focus is actually in quantum computing for finance. We have extensively just started looking into this area. Why? Because this area is full of hard problems. Of course, you have in optimization, Monte Carlo sampling, stochastic differential equations, machine learning, and so on. So on these hard problems, again, we have to just invoke both classical as well as quantum together, both the computing paradigms together to solve these problems. And of course, while just addressing this, I think already it is well known. It's even documented in the papers and all the videos on quantum finance and other things. So it actually absorbs 3 main pillars: quantum optimization, quantum machine learning, and quantum amplitude estimation. So all the things actually just fall into various problems, various different problems which has to be addressed in quantum computing for finance. So therefore, we have just taken this area. And because the one good thing is, even though we will be focusing on areas the problems related to portfolio optimization, option pricing, risk analysis, and regression, and of course classification. Again, of course, you can just make out which one is actually the optimization and which one is machine learning. And these option pricing and risk analysis are related to quantum amplitude estimation. So these algorithms, when we just have some new and enhanced algorithms, we can just use them across domains, basically. That's the beauty of these very rather rich pillars, basically. That's why we have just chosen, even though we are not finance experts. Of course, there is a very strong BFSI group, banking, finance services, and insurance group, basically, in TCS. That is one of the main pillars. But ourselves in quantum, actually, even though we will be collaborating with them, actually, and to just work out this problem. And also, just by building some of the POCs, may not be directly into this quantum, but even in the other domains, we are moving towards what actually is repeatedly just spelled out in the news items or in various talks or the forums or the collaborations, the quantum readiness. That means even though we may be a little far away actually in terms of actually just solving a real business problem, but we have to be ready. That's the quantum readiness concept. And we are also just gearing up towards that actually. Just, I think, this is one of the last technical slides, basically. I mentioned about quantum amplitude estimation. So this quantum amplitude estimation, actually, this is the circuitry. And it involves, this is actually just, I'm not going to the details, but if you just see, when you say quantum amplitude estimation, basically we are trying to just find out some expectation value or whatever it is. So that's we can just work out basically. So only the statement I wanted to just make is this is a phase estimation algorithm applied to a Grover kernel. That means we always just talk of 2 dual algorithms in our quantum algorithms regime, Grover and Shor's algorithm. It's a combination of both. And this quantum amplitude estimation actually is very, very important algorithmic primitive basically in the quantum computing for finance sector. And also using this quantum amplitude estimation, we can beat the Monte Carlo stuff, means the particle Monte Carlo stuff, quantum Monte Carlo just technique through what is called as quadratic speedup, basically. For example, if you are just simulating a number of paths for actually, let us say, option pricing, if 10,000 paths are required, then with 100 paths, square root of 10,000, with 100 paths, you can just get equal or the same amount of accuracy with the quantum amplitude estimation. So just in the interest of time, I'll just stop at this stage. And because, of course, there is a beautiful video also by Professor Roman. I think if you just go through, I think you will get all the things. So now I'll just, it's an intermission, basically. I think then we will go to the actual implementations and some more concepts. So this is actually believed to be the last written blackboard of Professor Feynman. So what I cannot create, I do not understand. So therefore, actually, in order to, fortunately, in this this time, even though we may not be able to just put experimental setup or test beds, whatever it is, at least we can just use various SDKs and the software platforms available to get a feel, build something and get a feel. This also just shows that I think those who just do it, actually, they might have understood very well. So with that kind of a precursor, I will invite Sayantan, who actually just does all sorts of implementations and also create a lot of new ideas to just take over and then steer the show. Thanks for your time. And then after the end of the session, again, I will come back. Until that point of time, I will be a spectator or the listener.
Thank you, sir. I'll start sharing my screen.
Yeah.
I hope my screen is visible now. If someone could please just indicate.
Sayantan, I can see actually.
Okay. Good evening, everyone. So what we are trying to do here today, what the motivation behind this tutorial is that we'll be solving a problem end to end. So there won't be much theory involved, just the minimal amount which is required to formulate the problem and solve it using quantum. But other than that, we'll be focusing on the implementation mostly. So the problem we have formulated for today is a variation of the subset sum problem. And we will try to solve it using qaoa, which Dr. Girish has just mentioned about. And I'm sure more eminent people than me have covered definitely over the last few lectures. So the problem statement is such that we have been given a set of numbers, and those numbers, they are real numbers. So they can take negative values, they can be fractional, anything. Just the limitation is that they cannot be complex. And the set has a cardinality of n. So there are n number of elements in that set. Along with that set chi, we have also been given a scalar number, which we have denoted here by capital S. What the objective of the problem is that from this set chi, we have to find out a subset of it such that when we have that subset, the sum of all the elements in the subset should be very close to S. I mean, as close to S as possible. So we want to find the subset which we could say approximates the value of S in terms of its sum. So we can clearly see that it's an optimization problem. Specifically, it's binary optimization. So any subset can be constructed from chi using a binary string of length n, where the binary string, of course, will consist of zeros and ones. For every element in this set, Si, small si, we will have a bit corresponding to 0 or 1. If the bit is 0, that means that element Si will not be included in the subset. If the corresponding bit is 1, that means it will get included in the new subset. So first, what we have done is just imported a few packages. For the purpose of this tutorial, we are using Qiskit, but we have tried our best not to use any Qiskit specific functions. That is, we know that Qiskit provides a variety of great optimizers, but we have not tried to use them because if one tries to move from one tech stack to another, say if someone wants to implement those on penny lane, then the same optimizers or of the same quality are not available. So we have used very, very generic functions here so that portability of the code is possible. Again, that is another thing which is very important in industry. So we have tried to take care of that also. Coming back to QAOA, which we have used to solve this problem again, we know that for QAOA, we have to create an ansatz, a trial state with which we have to find the expectation value of the problem Hamiltonian. In Girish's slides, the problem Hamiltonian was given by HP, but here it has been denoted by HC, just a difference in terminology, but the things are the same. So the first step in QAOA very highly is to bring all of the qubits in equal phase superposition by application of Hadamard gates, because we know that conventionally, whenever we initialize a qubit, it's always initialized to the state 0. So application of Hadamard gates on all of the qubits have been captured here. And after that, what we do is QAOA takes the number of layers as an input. So it's a multi-layered circuit. And each layer consists of application of an ansatz, which depends on the problem Hamiltonian. After the problem Hamiltonian ansatz has been applied, we also apply some kind of a mixing Hamiltonian to the circuit. So those portions have been captured here. So when the problem Hamiltonian is exponentiated and scaled with a factor, with an optimizable parameter of gamma, the corresponding circuit is extracted. We know that this part of the equation, it's always guaranteed to be unitary for any symmetric matrix HC. And after this problem Hamiltonian specific part, we apply the mixing Hamiltonian, which takes another parameter of beta as an input. This is just one layer of QAOA. Similarly, P-1 other layers are also appended to the circuit, where of course the number of layers we consider is P. P again comes from the traditional variable that was used by Farhi et al. When they defined this algorithm. So we will first try to formulate the problem in QAOA. Just having a mathematical natural language formulation, like as we had discussed, would not work. So as discussed previously, we will try to convert the problem to the QBO formalism, or equivalently, when we replace the binary strings with spin values, we can also consider that to be the Ising formulation. What we do for that is we start with a very, very simple observation that if we are given a subset of the universal set chi, and the subset again can be characterized by a n-length bit string, and the bits of that bit string, they are given by the variables xi's, where we vary the iterable I from 1 to n. And corresponding to each element, again, xi can either be 0 or it can be 1. So if we have that information for a subset, we can easily find the sum of the elements in a subset using this kind of an equation. So we'll just multiply the value of that element, the value of the real number, with either 0 or 1. Again, if the element is included in the subset, then xi would in that case be 1. If that element is not included in the subset, it would be 0. And in that case, we know that the product of si and xi would be 0. So using this equation, it's fairly straightforward to calculate the sum of all the elements in the subset. But what we can do is we will be replacing these xi's with Z matrices. So we'll come to what Z matrices are. It's not just a direct replacement. We have to take care of the tensor products, appropriate tensor products. So for every ith element, suppose we have a string of tensor products involving only identity matrices. For the ith element, we will replace the identity matrix with this kind of a Z matrix. And to define what the Z matrix is in this case is, it's nothing but a scaled and translated version of the poly Z matrix. So we know that poly Z matrix is a diagonal matrix which has the elements +1 and -1 as the diagonal elements. But when we scale it as such, when we subtract it from the identity matrix and scale it properly, the first diagonal element becomes 0 and the second diagonal element becomes 1. So these are kind of like the binary variables that we have in QBO. We know that Xi's can take either 0 or 1. So we have done nothing but translate and scale the problem to our classical domain. I mean, our classical understanding of yes or no. So this might be a little difficult to visualize. So we have tried to capture a very small example considering only 2 elements. So if our original set, universal set chi had only 2 elements, S1 and S2, then how would we calculate this matrix H, which is nothing but a quantum mechanical Hamiltonian counterpart of the sum of the variables in the subset? In that case, what we would do is we would multiply the element Si with these matrices. The tensor product of the Z matrix, which we have defined here, with the identity matrix. Here we see that the first position contains the Z matrix because we are considering the first element here, it says 1. And to this term, we add the second term, where again we have the value of the second element from the set S2. And since we are considering the second element in the tensor product corresponding, the second position is filled by this Z matrix. And if we expand that out, it's fairly trivial to see that we'll get this kind of a matrix where the first element is 0, second element is S2, which directly carries over from here. The third element is S1 from this, and the fourth element is S1 plus S2. So we see that if we have a set with only 2 elements, we can construct only 4 subsets from that set, 4 kinds of subsets. Either the subset will be an empty set and the sum for the elements in an empty set is 0. So that is something which is captured by this first diagonal element. We can have a set which is given by 0, 1, say, which means we include only the second element and not the first element. In that case, the sum of elements would be S2. Similarly, another possibility is 1, 0, first element included, second element not included. In that case, it would be S1. And the last case where we include both of the elements, where it can be an improper subset. So the subset can be exactly equal to the set also. So if we include both the elements from the actual set, then the sum of their elements would be S1 plus S2. So we see that in this kind of a formulation, the diagonal of the matrix captures all of the possibilities. What we just need to do is we need to capture the actual eigenvector and the corresponding eigenvalue. So the eigenvalue for that, suppose it's this element, it should exactly match with the target of S that we have set for us. If we are able to do that, if we are able to identify the eigenvalue, we can find out the corresponding eigenvector, and the bit string corresponding to that eigenvector would directly give us the solution to our problem with some classical post-processing. But it's not just enough to find out the sum of all the elements in a subset. We also need to impose the constraint that the sum of the elements in the subset should be as close to S as possible. So what we do is we try out a natural mapping to the quadratic domain. This part of the function, it again, it has been taken from here. It's the sum of the elements in the subset. We subtract from that the target scalar value that we have been given S, and we square the entire matrix. What that does is it creates a kind of convex function. And we know that it's very easy to optimize convex functions because they have a clear-cut minima or a maxima. in this case, we are mapping the problem solution to a minima. So we'll be trying to minimize it. So whenever this value of the sum of elements in the subset becomes exactly equal to S, we know that in the result of H cost in that case, if we think of the classical value, scalar value would be 0. Any deviation from that value would increase the would increase the value of this function. So all of these values again will be captured along the diagonal elements of the matrix, and it's still an eigenvalue finding problem where we just have to find the minimum eigenvalue. And as we might recall, finding the minimum eigenvalue is exactly what QAOA and VQE and variational algorithms like those do, because we try to minimize the expectation value of a Hamiltonian given some trial state. And we also know that the parameters to obtain a proper state can be varied using some classical optimizer. So I know we had said that there wouldn't be much math, but a little bit of it was necessary to set the problem straight. And if you could please just bear with me a little more, what happened is this cost function that we have, it's a fairly simple cost, but to create a circuit out of it, we'll have to simplify it a bit more. So although this part of the equation looks a little intimidating, it's a little long, but trust me, it's just simple simplification. So what we do is we have carried over this equation from here to here, and we just expanded it out. It's a polynomial, right? It's a quadratic polynomial. So we'll expand it out as this square term. It's just a binomial expansion. The square of the first term minus this cross term that we have with the scalar value provided, which is S, and all of the possible sums of the elements of the possible subsets. And we have a third term here, which is purely independent of the solutions that we are trying to find, which is just a square of the scalar value. Again, all of these are matrix elements, so we can't have a scalar value to be added to a matrix. So it's also been converted to a matrix by multiplying with a proper dimensional identity matrix. We see that we still have another quadratic term here, and within that we have a summation. So it's not just one term, a summation of many terms has been squared. So what we do here is just expand out that term also. This step is a bit notable because so far what we have had is we had individual poly Z terms, or the scaled and translated poly Z matrices, the Z matrices. But when we expand this term, we also get coupling terms. So we see the term Zi, Zj, which it's very unintuitive, because if we think of the sum of elements in a subset, it shouldn't really depend. It should really depend on the value of each element. It should not depend on the value of two elements together. So although it's a bit unintuitive, this is what the mathematics tells us. So we will go ahead with it. Next, what we have done is we have left out all of these scalar terms from the equations, because as we know, scalar terms, they don't really change the results of optimization. They just act to translate the solutions, the cost of the solutions, in fact, not the solutions themselves. So since they don't interfere with the solutions, we thought of ignoring them for simplicity. Also, these kinds of terms, they are not captured in the circuits, because if we try to find the corresponding circuit for this term, it will just be an identity matrix, which does not really do anything to the circuit or the state of the qubits. So this has been straightened out to some extent here, but we still can't construct a circuit out of these Z matrices. We'll have to convert them back to poly Z matrices, because to construct the ansatz for QAOA, we know that we have to exponentiate these terms. And we know that the exponentiation of the poly Z matrix is just the RZ gate. And exponentiation of coupling terms involving two poly Z matrices, they will be taken care of using ZZ interactions where we have a C0 gate, then we have an RZ gate on the target qubit and another C0 gate to follow it up. So we, again, just as we had moved from the poly Z matrix to the Z matrix, we'll move back to the poly Z matrices by an inverse transform. And the final terms that we get are captured here. So this is the term that we have for individual poly Z matrices. So these terms will form the parameters for individual RZ gates. And this term that we have here, the cross terms between the ith and jth elements, they will form the parameters for ZZ interactions, which we also sometimes call the RZZ gate or RZZ, whichever one seems to prefer. So that is all the mathematics we needed to take care of this problem. What we do next is we create the circuit corresponding to this cost Hamiltonian that we have just defined. We know that the circuit for QAOA, again, we start with n number of qubits, but those qubits have to be brought into equal superposition. So we first have to apply the Hadamard gate on all of the qubits. Next, we have to apply the p different layers. That is why we initialize a for loop, which goes from 0 to p minus 1, or from 1 to p, whichever can be visualized more easily. And within that for loop, what we have to repeat multiple times is application of these two unitaries. Not unitaries, but the gates corresponding to these unitaries. So first, we will be applying this unitary, where, as we recall, we have to apply single qubit gates, which are RZ gates. So we do exactly that by iterating over all of the possible qubits. That iteration has been taken care of by the for loop here. And the parameter for this circuit, for this RZ gate, it should be the optimizable parameter that will get optimized by the classical methods times a parameter which comes from the problem itself. And that parameter has been shown here. So we have minus times the square of the set element value that we had, and that has been scaled by a factor of 2. Plus we have the scalar element, the target value that we need to optimize it to, optimize the sum of the final subset elements to. That has been multiplied with the individual set element values. And there is a third term here, which is the value that we are considering, the ith set element, that has been multiplied with the sum of all of the elements in that set, in the actual universal set, excluding the ith element itself. So we'll first calculate the sum of all the other values in the universal set and subtract the corresponding set element from it. And when we add all of them together, of course, we'll subtract this because of the minus term involved here. We will get the theta parameter for this RZ gate. We'll multiply them. This parameter X will signify nothing but this gamma, which is again an optimizable parameter, just to reiterate. And if we do that, we have taken care of all of the single qubit terms. Now we have to take care of the coupling terms. And that is not very difficult anyway. What we just do is we run 2 more loops, one loop inside another, a nested loop. Both of them iterate over all of the possible qubits in the circuit. And the parameter, the non-optimizable parameter for the RZZ gates should be nothing but the jth element of the set multiplied by the ith element of the set, and the product has to be scaled by a factor of 2. So that is something we have captured here. That is the theta, the parameter for this RZZ gate. we haven't really used the RZZ gate because not all of the SDKs have support for that. So we have broken those down to CX and RZ gates. The consideration that we have made here is the assumption is all of the rotation gates, RX, RY, RZ, along with the C0 gate, they form the universal gates for this kind of a quantum computer. And we know that whichever gates any SDKs provide, they can always be represented in terms of the rotation gates and the C0 gates anyway. So as we had just described, we'll capture the RZZ terms as a C0 gate with the jth qubit as a control and the kth qubit as target. After that, we'll apply a Z rotation on the target qubit, where we will have this theta term as a parameter, but that theta term will be multiplied by another parameter, which again is this optimizable term gamma. And we follow it up with another C0 gate, where again J is the control qubit and K is the target qubit. This is fairly standard for many of the QAOA algorithms or problems that we try to solve. Yes, sorry.
Sorry to interrupt in between, but I just have a doubt here. Theta has been assigned two different RHs, like in the first set of the coding and in the second set of the coding. Is this the way of doing it, or like usually when we write any programs classically, we do not assign the same variables, right?
Right, but Python, as we know, is a dynamically typed language, and the value of theta that we have defined here, it gets used up here. And once this loop is completed, we do not need this value of theta anymore. So we can reinitialize the same variable theta to another value, and that also gets used up within the scope of these two nested loops. So they don't interfere with each other.
Okay.
And doing this has another advantage of not having to initialize another variable.
Yes.
That also saves some space.
Memory.
Yeah, exactly. Negligible, but it's there.
Yes. Thank you.
Sure, no problem. Once we have captured the RZZ interactions, the ZZ couplings, we are done with the problem Hamiltonian part. After that, it's fairly standard QAOA, where we take care of the mixing Hamiltonians, and we know that the mixing Hamiltonians for vanilla QAOA is nothing but an RX gate applied to each of the qubits. Now, this is the standard mixing Hamiltonian. There are more efficient mixing Hamiltonians proposed for different kinds of problems, but for the implementation that we have here, we are not considering those. Right, so now that we have constructed the circuit, at least define the method for constructing the circuit, let us take an example and try to visualize the circuit that we have. So what we say here is the universal set that we had, the chi, suppose that has elements of 1, 3, 5, and 7. And the limit, the parameter S that we had, the sum of the subset values that we are aspiring for, it has been given to be 8. So analytically, we can see that the subsets can either be consisting of the elements 1 and 7, or another subset, another efficient subset is possible, which considers the middle two elements of 3 and 5. Those are the best solutions that we can have for this problem. So I'll just run this cell here and this one too. And what we will try to do is we will try to visualize the circuit for only single layered QAOA implementation. So we'll just call this function from here and get the circuit. We'll print it out. I'm sorry, even if I increase the zoom level, the circuit doesn't get maximized zoomed much. I'll still try to explain what's in the circuit, although it may not be very legible. So again, we start with the Hadamard gates on all of the qubits. We have 4 qubits here because we have 4 elements in the universal set. And we next we apply the RZ gates, which are nothing but the individual terms in the problem Hamiltonian, followed by the RZZ terms, So this one together, these three gates, the first C0, the second RZ, and the third C0, together they form one ZZ in coupling interaction. So we have repeated that for all of the possible combinations of I and J. We know that there can be only n square maximum combinations of I and J if we allow for repetition between I and J. If we say impose another constraint that I cannot be equal to J, then it reduces to n into n minus 1 minus divided by 2, those many interactions. So the circuit depth, as we see here, it has been restricted to order of n squared. It's not exponentially deep. So that is something that noisy intermediate scale quantum devices can handle pretty easily. And within these barrier values, again, these easy interactions have been captured. After those coupling interactions, we apply the mixing Hamiltonian terms, which again are just individual X rotation gates on each of the qubits. Since this is only for one single iteration of QAOA, we could just perform measurements on all of the qubits after this. Just a point to note here is when Qiskit measures the qubits, if we use the inherent measurement functions, what it does is it considers Q0 to be the least significant qubit. But in our kind of formulation, we have considered Q0 to be the most significant. So the measurements have been performed in reverse. So the most significant is measured first and so on. That is something that can be taken care of using standard Python code. Another thing to consider here is, since we are dealing with a combinatorial optimization problem, we need not depend on the measurement values that we have from the circuit to find out the cost of a solution, a candidate solution, not the exact solution. So to find out the cost, we can just use a classical cost function as we have used here. So if we have a state, a binary string, say 0, 1, 0, 1, if we move back to the example, if the binary string was 0, 1, 0, 1, that means this element 1 would not be included and this element 5 would not be included. And 3 and 7, these are the only two elements would be included. And from that, we can simply calculate that the sum of 3 and 7 will be 10. It can be classically calculated. We don't really need to depend on the actual measurement probabilities to calculate them. But when we move to other problems which are not combinatorial in nature, maybe some chemistry problems, then it becomes imperative to use the actual measurement probabilities instead of defining a classical function to calculate the cost from a state. And once the cost of a state has been calculated, we run the circuit multiple times. In this case, we have defined the number of shots to be 100. So we calculate the cost from all of those 100 measurements. Each of those 100 measurements would give us a bit string. The cost for all of those bit strings was calculated, and the average of all of those 100 costs was taken, and that was passed on as a cost for the classical optimizer. This is also again fairly standard. We have taken a value of 100 for the shots is because we want to demonstrate some good results here. But we will also try to show that it's possible to do with much lesser number of shots as well. So we'll go ahead and run these cell blocks. And this function get best state, what it does is when the optimization procedure has been completed and we have the actual values of optimized values of gamma and beta, we can run the circuit again for multiple shots. Suppose we run it for 10 shots at the time. And for those 10 measurements that we obtain, we can easily check which of those measurements has the best value. It's not very expensive to find out the cost of 10 states. So that is how it's conventionally done in QAOA. We'll run this cell also. And now we will run the classical optimizer to optimize this value. The cost that we are passing to it again is the subset sum, this function, which calculates and returns the cost. we have defined a list of parameters. Since we have defined the number of layers to be 3 here, it's just an arbitrary value. The general notion is higher the number of layers that we consider for QAOA, better is the accuracy, because the trotted path follows the actual adiabatic pathway in analog quantum computing. But I would like to make a controversial statement here, but that although theoretically using a higher number of layers is beneficial, but that also means that we'll be considering a linearly increasing number of parameters that have to be optimized. And we know that with the addition of each parameter, each optimizable parameter, the complexity of optimization increases. And it's very, very probable that the optimization will get stuck at some local minima or another, or even worse, it could get stuck in a barren plateau and not give us any solution at all. So for the parameter values, we'll need 2p parameters, because we'll need p values for gammas and p values for betas. So together we'll have 2p number of optimizable parameters. So we have sampled them randomly within a range of 0 to pi. And we have provided a seed value of 1905 here. This is just a small Easter egg. People may recognize that 1905 was the year of miracles for Albert Einstein, the so-called annus mirabilis. So just a random number. I wanted to consider this one. And we'll run the classical optimization. We see that it was fairly quick, because we used the classical optimizer Kobila, which is constrained optimization by linear approximation. And it does not really consider any gradients, but it uses some kind of heuristics and approximations to find out the actual cost parameters, the actual optimized parameters. If we had used some kind of a gradient-based method like, say, SLSQP, then it would have taken a lot more time to get optimized, but then we also expect better results from them. So these are the optimized parameter values that we have. I know that we are nearing the end here. Yes, Shreya. I'll wrap it up in a minute or so. Is that fine?
Yeah, yes, thank you.
And using these optimized parameters that we have, they are captured in the result that we were returned by the classical optimizer. Those have been used to calculate, to construct the final circuit. And we will run the final circuit, get the best state out of the measurements that we will achieve at the end of each measurement. And we get a solution of the bit string 1001. And we know that the bit string 1001 is a feasible and efficient solution, because it includes only the elements 1 and 7. Together, they give the give a summation of 8, which is the exact value that we were targeting. Just as an ending remark, we would like to say that there was another study that was carried out by Dr. Constantine from JPMC. He used to be from JPMC, but now he's at Wells Fargo. So he had compared this approach that we have shown here with another approach called the Grover optimizer, which works for fault-tolerant computing. And this is actually a method that was devised by JPMC and IBM together. And the comparison study can be found at this link. So the link and the notebook again will be shared with the participants for convenience. And that is all I had. Thank you. Sorry, I have been going on for a long time.
Thank you, Shantan and Dr. Chandra, for the wonderful talk and the tutorial. So I know we just have 1 minute for the next talk, but if it's okay, I would like to take 1 or 2 questions if there is any questions. So if you have any question, please unmute yourself and ask.
Shreya, if, of course, you can also compile the questions and then just send it to us. And if we can answer, we will just definitely just get back to you basically. And also, I think it can be a good learning for also, because there may be some very kind of curious questions which may just put our thought process also more sharpened actually.
Yeah, I have a small question, Dr. Chandra. Dr. Parmar, I have a small question. Am I audible?
Yes, yes, Dr. Panigrahi, you are.
You see, this optimizer, it is still classical, right?
Mm-hmm.
Okay. Now, see, I am not very clear where is the advantage coming. For example, when one runs a quantum simulator, is it because of this implementation of like control knot, these kind of things, and a matrix language? Is that the kind of thing which is giving advantage?
So there are two avenues of getting advantage here. First, the computation of cost that that can be done using quantum. So that gives us a speed up, because we know that quantum circuits can run in nanoseconds compared to classical ones. So other than that speed up, the other thing is these kinds of variational algorithms, when we use them for optimization, they give us better and better samples. So initially when we start, we had 2 to the power n number of samples which were possible, and all of them were equally likely. But as we start optimizing the parameters, the sample space keeps getting restricted, and it tries to give more and more feasible samples, if not the efficient ones. So that kind of a heuristic and stochastic nature helps the optimization process.
See, okay, but I'm still not clear. For example, in quantum, how this noise, how much of it, is reliable? Because all the unitary gates, everything would be affected, no?
Absolutely.
By averaging, because if the next step is different, it's very difficult to, if there's noise. So how much of it is reliable? Maybe because of averaging, these things cancel out.
Yes, noise does definitely affect the performance of the algorithms. And we haven't really carried out studies to benchmark the noise and performance against different kinds of noise, but other scientists have. And it has been shown that QAOA is more resilient to noise than BQA is, at least for combinatorial optimization. But sorry, I cannot give a very concrete answer.
Very nice talk. I really enjoyed it. Very, very nice. Very
Thank you, Dr. Panigrahi. Thank you.
Yeah.
And great to interact with you, sir. It's the first time I'm talking to you, so it's an honor.
I have a lot more questions. We can actually interact. Girish, we have met.
Definitely,
we can
definitely
interact in future also.
Definitely, I look forward.
Yeah, thank you.
It's an end to this session. It has been a wonderful session. Now, let's thank Mr. Pramanik and Dr. Chandra once again.
Yeah.
And it's time for the next talk. So thank you very much.
Thank you, everyone.
Thanks a lot for this opportunity.
We are looking forward for more collaboration.
Thanks a lot.
Okay.
We will look forward to it.
Yeah, Chiranjeev, you are already in.
No, yeah. Praveen, I think, let me see if he's there. Praveen, you're there?
Yeah.
Okay.
Okay.
Yeah.
Okay.
Good.
Hi, Praveen.
Hi, Professor Panigrahi.
Long time.
How are you?
We met in, where was it? We met
Bhopal and Bangalore.
Bhopal, I think Bhopal, and probably after that Hyderabad. I don't.
No,
Hyderabad, I couldn't come. Bhopal, yes.
Yeah.
No, Bhopal and Bangalore.
Bangalore, right?
Yes.
Bangalore also.
Yes. So at least West has done one good thing. It has united.
Yeah, the community. United the community. Yes.
That's right. Okay, so Kiran, yeah.
Shall we start?
Yeah.
Okay. Very good. So we are very pleased to have Dr. Praveen Bhalamuddi from IIT Madras giving this talk today. So to give a little bit of a background of Praveen did his BTech from ITBHU in the year 1997, and subsequently he worked and he did 2 masters from Ohio State University, and he finished his PhD in the year 2011 from Ohio State University. And after that, he was doing postdoc over there, and he joined the faculty of IIT Madras in the year 2018. His broad interests are in the area of quantum technology using centers in solid-state materials and nanoscale magnetic spectroscopy and imaging. His expertise is in optical and scan probe microscopy and magnetic resonance studies. Along with his collaborators, he pioneered a technique for gigahertz range spectroscopy of ferromagnets using NV center quantum defects in diamond. So he's going to give talk on that aspect that I read just now. So without further ado, I would hand over the floor to Praveen. Praveen, yeah.
Okay. Thank you, Chiranjeev, for that introduction. And I should thank both Professor Panigrahi and Chiranjeev and the coordinators for inviting me. There's a very nice summer school that you are doing here. I know I was hearing the other day, you're saying that it's a long one, so I'm sure all of you are getting exhausted. So I'll try to keep it short and not run too long tonight. So the topic of what I'll be talking today is how do we use relaxation of spins for spectroscopy and sensing? So this is obviously spin being the quantum mechanical object. And so people use this as a sensor. And so I'm looking at some sensing applications using spins. I hope people can hear my audio clearly. Let me know. And I'm going to stop my video also to conserve the bandwidth because I'm not sure about the spin network speed here. Okay, so the outline for today's talk is going to be, so first, as the topic of course is introducing this idea of spin relaxation, which is a very intrinsic part of magnetic resonance. So I'll briefly discuss magnetic resonance and the idea of relaxation and how it's used for sensing. Then we'll look at one particular implementation of this that we have been working on and how this can be used using NV-centered, which are these quantum defects in diamond. And you have heard a few talks on these already. So I'll give a little bit of a brief introduction again for those who maybe not have attended the other talks. And finally, I'll share some of the ideas of how we are using relaxation, spin relaxation, which is usually seen as a bane and, having these technologies, how we can actually make use of it for doing some nice work, specifically in spectroscopy. And so with that, let me get into the talk. The first is, of course, magnetic or spin resonance, because this is at the heart of what I'll be talking about. And this has wide implications for spectroscopy, image, and nowadays for computation. Okay, and it's a very important field scientifically. It has had quite a significant impact. We have had 7 prizes over ranging from 1940s to I think the last one in 2003. There have been about 7 prizes awarded over. The first few were in physics, Rabi, Purcell, Bloch. I think Ernst and Wurtrich were for chemistry, if I'm not wrong. And then Peter Mansfield and Lavater were for medical MRI imaging. So that was in medicine. So you can see across a wide range of fields it has had, and really Erwin Hahn should have also won, I would say. It's unfortunate that he didn't, but a lot of his work is what we use for quantum computation and even in all of these other things.
Just interjection, Professor Anish Kumar was giving a talk and he mentioned the same, that Hahn should have won.
He definitely should have won. I think it's a bit sad that yes, even his work keeps becoming even more and more important now. And these are of course cartoon representations, and I'm not getting into the details of this, but just some pretty pictures to catch your attention, but also to illustrate the idea that this is a very widely used characterization tool, spectroscopic tool in chemistry labs or pharmacy and every place, where you need to have chemical identification or understanding chemical environment. And of course, as a medical diagnostic tools that sometimes scares people, especially if you're claustrophobic, but nonetheless, it's a very valuable tool that has, for medical diagnosis. And now, of course, it's new avatar. We are starting to talk about quantum technologies, the use of this for quantum technologies. And the idea here is that there is a tremendous history in magnetic resonance in controlling quantum systems. And that's where we'll see a little bit about Hans' work also in controlling quantum systems, which is very valuable. And this is now being used by other platforms as well, not just spin-based techniques, but even superconducting or ion trap-based. All of them now use some of the techniques that have been developed over these last 60, 70 years in magnetic resonance imaging. And as I said, you have heard quite a few excellent talks already within the summer schools. These are just the ones I think I at least attended briefly, if not completely. And there might have been other ones also. So I apologize in case I'm missing out somebody, but these are the ones at least I saw. And so you had Professor Kasturi Saha from IIT Bombay. She talked about optically detected magnetic resonance, something that I'll also discuss about, and an overview of this term that you will hear in my talk as well, NV centers in diamond, how to use them for quantum computation and sensing. Then we had Professor Suter from Germany. He talked about using quantum registers of NV and nuclear spins. So this, of course, I'm highlighting this in optical detection of magnetic resonance. But then we had Professor Anil Kumar from ISC, so who works on conventional NMR, which is where things started. And even for quantum computation, that's where it started. And he discussed about that as well. So these are inductively detected nuclear magnetic resonance. And really a lot of stuff that people are borrowing now were developed, for these NMR techniques. And so we have a lot to thank the NMR community for that. And then we had Professor Tanmay Chakrabarti, who I think is one of the alumni, and he was talking about charge state control of NV centers, how you can use that also. And then finally, we had Professor Suddho from IIT Bombay again, who talked about electrical readout of spin resonance and how to use spins in silicon. So these are as opposed to, let's say, NV center spins that I'll talk about. So, but nonetheless, it's a similar architecture trying to make use of similar concepts. And so some of these ideas carry there also. So let's get into magnetic resonance. So with that introduction of what you have seen, and also the idea is what is different, because you have already seen so many talks. So what's different that I'm going to be talking about? So part of my showing was also how they were all mapping out different areas of the field, but nonetheless, each is a different important part. And so what am I going to talk about? I'm going to talk about something, relaxation, which is very intuitive. And we'll come to relaxation. First, let's understand briefly, hopefully this is a quick review for most of you students out there. So essentially we can imagine the simplest two-level system, a spin half in a magnetic field. It will be a two-level system. And the basic Zeeman term, which is the Hamiltonian. There's the simplest Hamiltonian we can imagine. And there's the interaction of the spin with the field, which is B dot S. If you have a microwave, which matches this energy splitting, then you will have resonance. That is when you'll cause transitions, resonant transitions. And of course, as I said, this will be the resonant condition for that. So there are two ways to visualize resonance, right? There are two ways to visualize. One is in the time domain and one is in the frequency domain. If you talk about the time domain, then of course you can write the evolution of the spin with this Hamiltonian. And so hopefully all you students will know how to do that. So you can write the Hamiltonian, and you can, of course, nowadays, lots of software packages are there, and you can see how it evolves. So the details of what I'm showing you here are not important, just a picture to illustrate that you can follow the time evolution of the spin here. So that's one way to visualize. And also, please remember that this requires two magnetic fields. One is typically called B naught. In magnetic resonance community, the B naught, which is the static magnetic field. And then we have B1, which is this photon that you're applying. This is the alternating magnetic field. So that's typically in the range of microwave to radio frequency for magnetic resonance, depending on whether you're talking of electron spin or nuclear spin. So this is what is causing. And obviously, if you know what quantum mechanics, you'll need something perpendicular to the static field that is causing the to the quantization axis. So in this case, the B naught is what is setting the quantization axis. Let me make sure I get my laser pointer out here. So the B naught is setting the quantization axis, and then B1 will be perpendicular to that. And that's when you can cause these transitions and you can follow the time evolution. The key thing for us to understand is that the spin will be processing about the total magnetic field at any given instant. So whatever is the total magnetic field at that point, it's going to be processing about that thing. And so this precision is a key word when you're talking about time evolution of the spin in a magnetic field. The other way to visualize is, of course, spectroscopy, which is looking at these transitions in the energy domain or in the frequency domain. And so here what you will see is not the energy levels, of course, themselves. So you could have this Hamiltonian, you can solve it, you can get the eigenvalues, and you will know. But of course, in an experiment, what you measure is not the absolute energy. What you're going to measure is the transition. And so that's what you'll see is the separation here. So these are in some normalized units where I'm saying omega naught is the resonant frequency, let's say, where I'm having the resonance. And so what, for now, the details of the signal are not important. We'll come and look at that in a bit. But typically what you'll see is a signal that looks like a Lorentzian line shape, okay? And again, these come from the solutions to simple harmonic oscillators, if you're talking of a two-level system. And classically, you can solve the block equations and you will come up with these kind of a solution for what the signal should look like. But you'll see a Lorentzian curve. And so typically, so that's the most fundamental one. Of course, you could have other line shapes as well, but we'll fix with the simplest one for now. What is going to be, so yes, so first is this is spectroscopy. So this is like a fingerprint that is used. So changes to this line, to this profile is what people use to understand changes to chemical environments, so shifts of frequency. And the other important thing is also this width. What is the relaxation rate? So if you have, so as you know, this you can think of it as a simple harmonic oscillator. And if you're going to have if you have this curve, this resonance curve, the width of this resonance curve will be related to the dissipation or the damping, or what we'll call as the relaxation. And this here is proportional to the relaxation rate. The width will be related to the relaxation rate. And I'll come and I'll discuss this relaxation rate in more detail. So don't have to worry right now. So, but it's important to understand that this width, so this gives the relaxation rate, and that also carries quite a lot of information that is useful that we can use. So with that in mind, so that's the magnetic resonance. So with that in mind, we will get into the sensing part of it and how relaxation comes into that and what does relaxation do. So since I'm talking about sensing in my talk. And so the sensing that we are talking in magnetic resonance is magnetic sensing. So this is a spin that we are talking, which is at the heart of magnetism. And so the sensing that we typically do using these kind of spins is magnetic sensing. There are different modes in which you can do this magnetic sensing, and relaxation plays shows up differently in each one of them. And so we should understand how it plays a role in each one of these, good, bad, or ugly. So we should try to get a grip on it. So the first one is this from a very nice review article that I would recommend from a Deegan group that has been, the citation is here. And so the first one is where what's called the continuous, or I have named it continuous wave spectroscopy for the lack of a better term. But the basic idea is similar to what I was showing you earlier, that you have some microwave. So you have a frequency, a photon frequency or a microwave frequency that you're sweeping. At some point you hit resonance and you'll see the resonance curve. Don't worry about the negative sign of the peak. That depends on the detail of how you're doing the measurement. In this case, we are doing what's called optically detected magnetic resonance. What's more important is the that there is a resonance that is happening. And so in this case, if you are to measure a magnetic field, the way you would measure is you would monitor for the shift of the resonance frequency. So that, of course, can be too slow, because if you have to sweep each time the entire thing, that may take a long time. But let's say if you said the magnetic field is not changing too much, it's changing within this width of this peak, then what you can say is you can sit out here and you can sit at the steepest slope, the point of the steepest slope, and you can just monitor the changes of amplitude. And this is, of course, a trick very commonly used across many such measurements if you're doing AFM or pretty much anywhere, or even any LCR, wherever you have such resonance curves. This is a very standard, even in your communication circuits. So there's a very standard thing that is done, that you do an amplitude detection using this resonance curve. And so you can do this and you will get some kind of sensitivity. And the thing here, though, is that typically this will be limited. In the best case scenario, this will be limited by something called as T2 star. And I'll come and discuss in the next 1 or 2 slides what is T2 star. This is just my way of introducing these notation. But in all likelihood, you'll have to be careful that there are no nonlinear effects, that you're not sweeping too fast. So there are many other things that can keep you from reaching this limit even. The next one is called Ramsey sequence. Okay. In the Ramsey sequence, this one here, what you're doing is you're applying the microwaves continuously. So it's a steady state experiment. So you keep applying the microwaves continuously and you cause some steady state changes of population. That's what you're monitoring. Here in Ramsey sequence, you go into what's called the pulsed mode. In the pulsed mode, what you will do is you control the microwaves in the time domain. Okay, so you control your spins in the time domain. You do a controlled rotation. And so the first thing, what I'm not showing you here, is you initialize it somehow. So let's assume that you have initialized into some state, in some pure state, either 0 or 1, whichever state you want. And then you apply a pi/2 pulse. This pi/2 pulse in the block sphere will bring you into the superposition of the 2 states, or the 2 pure states. So you'll be in the XY plane. And then the field is assumed to be along the Z-axis. So you're on the spin is in the XY plane. The field is along the Z-axis, and you're going to be precessing in the XY plane. And what you're seeing here is that sinusoidal oscillation, the precession of the spin in that field in the XY plane. When you do this, again, you'll see that there's, as you change the magnetic field here ever so slightly, you're going to see that you will have a shift of the frequency. So you can, of course, monitor, either measure the frequency itself, either measuring this long time, or if the field is not changing too much, only slightly, you can sit at one of these points and monitor the change again of the amplitude. So whichever, I mean, if shift is big, maybe you'll have to measure more. If it's small, then you can sit and measure. So this is another way of monitoring the phase accumulation that happens as the spin is precessing in the block sphere in the XY plane. There is another one, the third one, which is called relaxometry, and this is what I'm going to be focusing on. And this is where you monitor the changes to the spin lifetime. And so this here again is limited by something called as T2 star. As I said, I'll discuss that. I'm just introducing the notation for now. But the third approach is relaxometry, where all you're doing is you're kicking the spin out of equilibrium and then watching it come back to equilibrium. So what you typically do is you just give it a kick. Either you completely flip it or you put it in the XY plane. And you just monitor how long it takes for it to come back to thermal equilibrium. And if you do this, normally, let's say if this is your curve, here they're showing that in the presence of certain what is called contrast agent, T1 contrast agent, there's a big, basically a magnetic moment. And we'll discuss how this change happens in that's part of the presentation here. But you'll see this big change of what is called spin lifetime, because how fast this magnetization decays. So here you have put it in some non-equilibrium state and it's decaying into some equilibrium state. So how fast it will decay to equilibrium state is a measure of the relaxation processes. And a change in these relaxation processes can also give you information and can also be used. And this is kind of the modality that I want to discuss. The next one, which won't be at the heart of what I'm doing, but nonetheless, since I'm going to be talking about magnetic resonance and the interest of, as we discussed, Professor Hahn, I should mention that this is the most actually important one that is being used currently, or most widely used, the Hahn echo sequence, which can give you even better sensitivities. Better sensitivity compared to the Ramsey sequence, let's say. And so what you get is, this is one of the biggest achievements in magnetic resonance, I would say. And at the heart of, you'll hear this phrase, dynamical decoupling schemes in quantum computation. This is a very commonly used thing now. And so this is at the heart of it. It has evolved into, a lot more sophisticated things, but this is still the basic unit of what they're all based on. And it's designed for countering the ill effects of spin dephasing due to inhomogeneous magnetic fields. And so I should thank my student Anshuman for these, for these animations here. But the heart of it is you apply a pi/2, and as you're seeing, this brings you into this XY plane. So I can start there. And then what happens is that the spins starts to dephase here. And the reason they're dephasing, or they're moving at different speeds. So imagine that either you could run the same experiment many times and you'll get a different answer. Or if you have many spins, an ensemble of spins, then each will vary at a different rate, because you have local magnetic fields that can be fluctuating on a slow time scale, okay? And so these could be fluctuating on a slow time scale. These could be even almost DC-like, or something slow compared to the resonance. And so these are sort of, then the spins is processing about the local field. So they're going to have different persistent speed. And this is the problem. If you're going to do a measurement, this becomes a problem, because you want to measure one frequency. But if each one is going to show something, a local variation, then as you can imagine, even a tiny bit of variation can soon lead to all these spins being dephased relative to each other. And to counter that, what Hahn suggested was this brilliant thing, is that just implement a pi pulse. Now, pi pulse here is a flip, as you saw. And I should point out this pi/2 pulse is, of course, because it's a pi/2, we are rotating by a pi/2 angle. And this in quantum computation language would be a Hadamard gate, and the pi pulse would be a Pauli gate. So you have these two. And then what you do is you flip it, but now the local fields will remain the same because they're slowly varying. And so now what was moving fast is behind now. And so it will again catch up in the slow moving. And at a certain time, if you ever let it evolve for the same amount of time, they will all focus again, and it will be sort of an echo of the signal that you had to begin with. And then you can measure this and say that what is your spin, okay? Or you can maintain your spin, or you can sort of figure out, you can maintain sort of your spin state longer by doing this. That's the basic idea. And you can use this actually for measuring magnetic fields, though the fields that you are measuring here are not DC fields. So let's say in the initial examples that I had shown for the Ramsey and all, we're kind of looking at a DC field. What you're measuring here is an AC field. And what you have to understand is that the echo is quite good, quite brilliant at canceling all the field components that are not at a particular frequency, that is the frequency of the echo itself. If you have a magnetic field that is varying at the frequency of the echo itself, then it will not cancel. In fact, it will enhance the effect. The precision, because of such a magnetic field, will keep adding and enlarge your signal. So if this is something you didn't want, then it's a problem. But you can engineer your system such that this could be the signal of interest, and then you could selectively filter out everything else, and you could measure only this signal. So let's say if you're measuring a signal from a nucleus spin, which is varying at this, so you can engineer so that nucleus frequency happens to be at this, and you can measure it. And so you could use this, and similar to this, you could sit at the steepest slope and you can measure this. But now we are not limited by T2, but T2 star, but we are limited by something called as T2, where you have removed some of these inhomogeneous effects. And so I should keep moving. I just noticed. So I should try to pick up the pace a bit. But the idea here is that we need to have a way of quantifying all these different things. I said T1, T2, T2 star. These are a way of quantifying this relaxation. So let's try to get into that. So the first is the mechanism for relaxation can be varied and complicated. I'll give you a little bit of an idea about that, but it's too hard. It's a very material dependent thing. You typically need temperature dependent measurements to establish the mechanisms. And these were some fantastic work were done right from 1940s and 50s in trying to understand. A lot of what we understand comes from there. The important thing for us is that it's usually dealt in a phenomenological way, okay? By using exponential decay of magnetization. That's what we model it as. And there are three in spin relaxation, you'll find three terminologies primarily. There are other ones also, but these are the three most commonly used: T1, T2, and T2 star. T1 is a spin lattice relaxation where the spin is up here. So let's say in the absence, if you had a magnetic field, let's say you're applying a magnetic field and you had spin initialized here, it would normally keep precessing about the magnetic field. But if you let it relax, let's say if this was the ground state, then over time, it would sort of slowly press us down to the lowest energy state. And the important thing to remember, this is called spin lattice relaxation because, or in terms of many times it's these days for quantum computation, it's also called amplitude damping. But this is along the quantization axis. But this requires a change of energy. And that's what you need to remember for yourself, that this will require a change of energy. Then you have the next one is the T2, which is actually, let me finish. So the change of energy, of course, means that the energy has to go somewhere, and the most obvious sink for energy would be the lattice, and that's where it goes, and that's why it's called spin lattice relaxation. The next one is dephasing, which we already considered. So this is called T2. In the absence, but typically what you will also have, as I said, is some inhomogeneous broadening that, you could have spatially, locally varying fields. That could, your magnetic field could be inhomogeneous, or there could be some other magnetic impurities, or the H1 field could be inhomogeneous. So all of these together add up to what is called the T2 star. And so these are the three time scales that we should be very aware of for our system. And this is, you must have seen in your other talks also, people discussing these things. And just because I had that heavy text, heavy slide, I should have some pretty pictures. And also to give you an idea that these things are in common use. So this is commonly used and very already used in diagnostic applications also. So I'm showing you some examples that I've taken. I'm not an expert by any means. These are just examples from literature that I've taken of where people are showing. So I think this is map showing for a multiple sclerosis patient, I think. I may be wrong about that, but I think that's, as far as I know, that's what it is. And so again, the details are not what I'm trying to go. It's mostly to show that this is already in use. This idea of relaxometry, that looking at relaxation as a means of understanding. So something, so what they have engineered such that either there's a contrast agent that only goes to the diseased part, or the diseased cells would have a different, parts would have a different lifetime for whatever reason. And so you could map out the lifetime itself. And you can use this idea of relaxometry is being currently used in relaxometry, okay? So as I said, there are 4 different ways of doing magnetometry I'd shown. And I'm now switching back to the relaxometry, which is going to be the focus of my talk. And this is already being sort of used. And this is, I think, a liver which has excess iron or something like that, some iron-related disease again. And so they are able to map out those regions by looking at the change of relaxation times. And so the main idea is that various protocols have been developed. Again, this is not my forte per se. I mean, a lot of work has been done in the diagnostic field. The key is to point out that this is already being used. And we should understand, I've been talking about these lifetimes. So why are we talking about these lifetimes, T1, T2, T2 star? What is the, how do you think quantitatively for us about these things? And so here I'm giving you an example of thinking about sensitivity of, let's say, a magnetic field sensor. Similar things can be written for other sensors as well. This is just one example from the literature that I've picked up. This eta here is the magnetic field sensitivity that they are talking, let's say, for an ensemble of spins. The ensemble comes here as N. And these details are not important for us. This will take a long time to explain. But just, I mean, something that you should consider for your protocol. You can have a look at it. You can stare at it afterwards also. And what I'm going to focus on is this part, the spin dephasing part that shows up in the sensitivity. And this is intuitive, right? If I go back to here, if I go back to this Ramsey sequence, what is limiting me here is this decay of the signal here. So this is decaying over a time scale of T2 star. I should have made that more explicit. And this is what is setting the limit. And if this keeps decaying, I can't tell at some point this the signal will go to 0 and I cannot measure it. And so that will limit how sensitively, because that can also tell you, you know, how accurately I can measure the frequency. If I can measure it for a long time, I can measure it more accurately. And so this T2 star is for a Ramsey sequence that they have given. Now, a similar thing can be written in terms of if you replace this T2 star with T2, and that was the achievement of going to a Hahn echo sequence. So if you have an echo sequence, and there are other things that make it even better than, you know, that can increase this time scale, can keep increasing, as I'll show some examples. But changing this T2 star to a T2 would already be a gain, because T2 is going to be longer than T2 star, okay? Which means in the frequency domain, if you're talking of rates, it will obviously be opposite. But so anyway, so increasing this time is important because that will mean that eta will become smaller, which will mean that you can measure a smaller field, which is what we want. We want something that is more sensitive. We want to be able to measure a smaller field. Now, the goal, as I will show here, is that T1, as you will see, is going to be longer than T2. So if we could put T1 here, so that will make it even more sensitive. So if you could have a protocol that is limited by T1 instead of T2, that'll be even better. And that's kind of the motivation for what we are talking. And so how do we think about T1 and T2 and why is what bigger than the other? So think about that. What you have is these relaxation rates here. And these come because of at the heart of this relaxation is fluctuations, really. And for any relaxation system, really, fluctuations at the heart of, you know, dissipation or damping, that you will have these fluctuations that lead to cause relaxation of a system. And these fluctuations could be anything. So you have thermal fluctuations, you could have physical motion of something, but the main idea is that, you know, you basically will have some other spin or some magnetic impurity, and it's sort of fluctuating around. So the field, because of it, will be fluctuating. And what they have found is that if you have these fluctuations in magnetic field around your, you know, your spin of interest, that is what causes the relaxation. And so so the KD here captures the magnetic interaction between some magnetic fluctuations, okay? Between the magnet, whatever is causing the magnetic, it could be some other spin or something else. So this captures the magnetic fluctuation, the amplitude of those. But what is important for us to see is that the T1 is caused by fluctuations at the resonant frequency itself, at omega naught. I mean, there is a component 2 omega naught also, but we will, so at omega naught and 2 omega naught. So it is being caused by the fluctuation that happen at resonance itself. And that's the key, that if you want to flip the spin, you basically need to have a spin relax, you need to have some transition, a resonant transition. And so this is that basically coming from that idea that you need to cause a T1, what you're causing is a spin flip essentially, right? And so you need to have some resonant excitation of, and so it happens because of resonant noise. The precession, on the other hand, in the XY plane, which is related to T2, can happen even by a DC field. And so even a DC field can cause this precession. And so you can write these expressions for spin relaxation, and these are called correlation, tau C, which is a very important parameter for each system. It's very hard to measure, but nonetheless, you can model and you can try to figure out, is a correlation time. So let's say if you have a liquid, you could have the tumbling of the molecules in a liquid. You could be moving around and you could have a Brownian motion, and that could give to a correlation time. In a solid, it could be some other thermal interactions or some phonons or something else that could give you correlations. So there are different things that could set this correlation time, but as a function of this correlation time, you can figure out what T1 and T2 are. And because the T2 has a DC component, as you go to longer and longer correlation time, you'll find that, which is the case in the solids, the T2 becomes much smaller than T1. The plot here is made for a nuclear spin. Even for electron spin, you can sort of write a similar thing. But the main message is that T2 can be much smaller than T1. And so if you go back to the idea of sensitivity, if you can put T1, then you can make it more sensitive. And that's kind of the idea that we are discussing. And so let's discuss the spin relaxation mechanisms. I won't have too much time. I'm keeping track of time here. So, and these are not as central to what we are going to be discussing later, but nonetheless, I should give you a general idea that how to think about spin relaxation mechanisms. And there are two ways. One is the energy level picture. This is more for the T1 processes where there needs to be a change of energy. And you can have different ways that you can imagine that you have a spin system. This is Ln that loses energy. So spin goes from upper state to lower state. The lattice gains that energy directly. You could have an Orbach process, or you could have a Raman processes. So all these different kind of processes, interacting with acoustic phonons and optical phonons, all of these come into the picture. And you can have these relaxation processes. But of course, this does not say anything about the mechanism. The mechanism itself comes from some unwanted, finally, you need some magnetic field. Ultimately, it's some change of the magnetic state. So you want a magnetic field, or there should be some magnetic field that causes relaxation. And the origin of these could be spin orbit coupling, or there could be a magnetic anisotropy that is being modulated. So let's say in the case of silicon, the T1 is set by silicon has these valleys in it, okay, in its band structure. And each of these valleys has a different G. So there's an anisotropy in the magnetic, what's called the G value. And so the gyromagnetic, and so that changes between the valleys, and that eventually leads to the relaxation. For T2, you could have spin-spin relaxation. So you have two electron spins could be talking. So if you have multiple spins of the same that you're measuring, those can be talking to each other, and fluctuations among them can lead to, you could have a spin, electron spin talking to a nuclear spin, sort of relaxing each other. Or as I said, for inhomogeneous broadening, you could have some inhomogeneous magnetic fields and impurities. So there could be many different regions. There's reasons. And there's not even, an exhaustive list. But these are sort of at a micro, the reasons why you could have, and this is kind of the energy level picture. So in the remaining time, let me come to the, so that was sort of, given the school nature and the tutorial nature. So that was the introduction to spin relaxation. So now let me come to a little bit of my own work with NV centers and how we use this system, or this idea of relaxation. So the NV centers have been covered thoroughly, I think. So I'll try to be brief. This one slide is probably covers mostly what you will need to know about NV centers, especially for this talk. So you have the NV center, which is in diamond, as I said. And if you have lots of NV center, it makes the diamond pink. That's what we are saying here. The main idea of NV is it's a nitrogen. It's a defecting diamond. Okay, so it's a defective diamond. And so what we have done is you have doped the diamond with nitrogen. So that's a substitutional. So you remove one carbon and you put. So this is the carbon tetrahedra, sp3 bonded in diamond. So you replace one with a nitrogen. So it's a donor with one extra electron. It's the negatively charged state of the center that we're interested in. So it captures an electron from somewhere else in the state, or you could do some clever manipulation to charge it also. So you could have a negatively charged state of the NV center, and these two together will form a spin triplet. So there's spin half together, they give you a spin triplet. And the spin triplet is at the heart of what we are talking. So this is what's called the ground state level of the spin triplet, and where you have the spin 0 and spin plus and minus 1. In the absence of a magnetic field, these plus and minus 1 will be degenerate. In the presence of a magnetic field, the plus and minus 1 will have a Zeeman splitting, but that's not as important right now. More important is there are two levels. So this is the two-level system, either 0 and plus 1 or 0 and minus 1. The key is it's a very stable two-level system. And very importantly for us, it can be optically initialized. You can shine a green laser on it and you can initialize it within a few microseconds. And that's almost up to 100%. And this really is a very fantastical aspect, especially if you compare it to, let's say, Professor Sudha was talking about polarization and electron spin of silicon, where they are using thermal polarization. And that's one of the reasons they have to be going very low, because the polarization will be small. I mean, among other things, there are other things also which help them by going to lower temperature. But if you rely on thermal polarization, the polarization will be less than, at room temperature can be less than 1% or even 0.1%. So you can have a huge advantage by having an optical initialization. I'm not I'll hurry through the next slides. I'll give you a little bit idea of why that happens. But for this talk, what's just important is to know that you can optically initialize it to a very high degree. The second thing is, of course, what is well known from the magnetic resonance community already is that you can control using magnetic resonance, this two-level system, because it's a spin system using, you can do a coherent control using resonant microwaves. The other important thing to know about the NV center is that it has a long coherence time, and not just coherence usually refers to the T2 time, but even the T1 time is fairly long. It's among the longest for a solid state spin. And this, again, these two together combined is this combination of everything is what makes NV so special. The third, of course, is that the big advantage is that it's related the same physics that enables this high optical initialization, which is the coupling of the spin and the optical properties, also allows you to measure with very high fidelity the spin state. So it's so good that because light measurements, this is an optical light measurement as opposed to, let's say, a microwave photon measurement. We have very good sensors for optical light. So you can measure with very high precision the spin state. And that's the big advantage. I won't get into the nuclear spin. This was talked about by Professor Suter, that you can have this hyperfine long-lived nuclear spin coupling that can give you nuclear quantum register. That's not of importance for this talk, but nonetheless important for technology. And then the fact that it's solid state and compatible with conventional materials is also important. So I think I'm not going to get into too much detail here. I'll just flash this, that there is, you probably have seen this before in other talks. So I'll just show this, that this is the full energy level diagram, and there's an intersystem crossing with a singlet state, which is what enables this coupling of light transitions, visible light transitions with the microwave or the spin level, okay? And the qubit or the qubit or the sensor that we are talking is in the ground state here. And so I'm not going to belabor this point already. We have done a fair bit. The important point here is that because you can read the spin state using a light, you can simply monitor the fluorescence here. And when it hits magnetic resonance, you will see that the light intensity will change. And so spin state 0 is bright, spin state plus or minus 1 is dark. Dark by, for a single spin, about 30%. In some of the other experiment with ensemble spin, it can be as less than 1%. But nonetheless, it changes, and you can measure this change sensitively. And you can say that you have looked at, you can optically detect the magnetic resonance. This is ODMR. And this is at the heart of, let's say, what a lot of the other talks have been talking about. And just to give you a quick idea that the sensitivity of the NV spin comes from this B.S term, of course, which is common to all spins. For NV spin, the hyperfine coupling that we are talking comes from this hyperfine term. So if you have nuclear spins, there'll be hyperfine term, and this is what gives you the nuclear memory. There are a couple of things that I don't know if anybody has discussed, but there are other terms in the Hamiltonian that can give you temperature sensitivity and strain sensitivity. Again, these are not at the heart of what I'm talking, but nonetheless, you should be aware that NV can do nanoscale temperature and strain sensing also. And again, I've covered this, so let me skip this. In the interest of, I'll take just 1 minute because I do this all with all students, and since there are a lot of students probably here, I should point out some things here. Maybe this is more important to you than my own experiments. And so this is a general schematic of how you can do that I've taken from one paper, but these are very common, very similar to what all of us do. Is you have a laser that comes through, and then of course it goes through different beam splitters. You sort of, this is what is called a confocal setup. You can, so you need some pinholes and it'll come through a fiber, which acts as a pinhole. But the key things I'll point out is there's something called as AOM, which is acousto-optic modulator. This creates nanosecond scale pulses of light, which can initialize the NV center. As I said, short pulses of laser light can initialize the NV center, and also are used for detecting the PL. So this is both. You need it for initialization and the readout. So it excites the PL which happens to mean they're red. So you will collect that. What is important for students to understand here is that the laser that is exciting the PL can be 1,000,000 to 1,000,000,000 times stronger than the PL itself that you are using for detection. So you need to do a very good job of cleaning up this beam. So there'll be a whole lot of filters here. So there's a dichroic mirror, there are other filters, but this is very crucial for you to understand that you have a huge background. And so you need to extract your signal out of that. And that's one of the things that you should be careful about. And so once you do that, then of course, that's what all these filters and other things are. And then you can have very sensitive detectors called as either single photon counters or avalanche photodiodes, and you can use those. And this is the other thing, that visible light has these very sensitive detectors that are not available in other frequency ranges, and we can use this to do the measurement. And the other thing for you to understand is that it is usually that if you're going to do interesting experiments, then you are going to be limited by noise. At least that's what I tell my students, is that if there's an experiment and it's not going to be limited by noise, it's probably not interesting enough for me, okay? And so it's very important for you to understand the noise in your system. And so if you're going to be doing a sensitive measurement, understanding noise in your system is a very important part. And I'm not going to go, it'll take a very long time. You can ask me questions later, but the idea is that for typical light measurements as we are doing, what you want to be limited is something known as the fundamental noise called a short noise of the PL, at least in the classical limit. Now we are talking about going beyond this classical limit of short noise. But let's say for now we keep it simple. You want to be limited by the short noise of this PL. But of course, there'll be about, 20, 30, there's not even an exhaustive list. Anything and everything and their mother and father will come and affect your measurement. So if you're going to do a PhD, out of 6 years, 5 to 6 years, basically till the last year, you'll be trying to figure out all these noises. And then in the final year, you'll get to figuring out and then doing what you wanted, getting to the result. So the one thing to say here is, so this is just an aside to show you how the schematic works and for the students to emphasize this idea that noise, paying attention to noise is a very crucial thing, and please do that. With that in mind, let's come back to the goal here of looking at lifetime and how we can use the lifetime. And so I can see the time. Chiranjeev, I'm going to be a few minutes over, but I hope that's okay.
Yeah, that's fine. Yeah. We started late. Yeah.
And so we are looking at spin lifetimes. That was our point, that how do we use the spin lifetime? And the first thing, as I said, is NV is good because the lifetime is long. And this is just showing you examples of long spin lifetimes in NV centers. Again, the goal is not to go into the details of each of these graphs. I'll give you some idea of what we are looking at. but we don't need to. What we need to understand is that this is the echo as we are talking, which is what is used to measure the T2, as I said. So each time the echo comes back, the echo, if you remember, can only cancel inhomogeneous, the fields that are causing inhomogeneous fields. If there are still some which are more or less static compared to the precision of the spin itself, if there are some random noises that are happening, the echo cannot cancel that. And so over time, the echo amplitude will decay, and that is what will give you this T2 star, or T2, sorry. And so you can look at this decay of T2 with the echo experiment. And this is measured at room temperature in Watcher group. And this was a fantastic early work where they have increased the lifetime by creating isotopically pure diamond, which reduces this hyperfine interaction with nuclear spins. So this is the double whammy of all our things. Interaction to nuclear spin can be good. It can lead to nuclear memories, but it can also lead to, relaxation. So you have to be careful in how you engineer your systems. But in a general thing, you can increase your lifetime by making isotopically pure diamond. Similarly, you could have an NV in a doped diamond, and you can, now they have been able to achieve even longer. So if you see, this is 2 milliseconds. Now they are reaching even longer lifetimes in the same, without even having to do this isotopic purity and all of that. Even in a standard diamond, they're able to reach. And of course, if you go to low temperature, and if you apply these echo protocols the way we are talking, the more sophisticated dynamical decoupling schemes, you can pull this spin decoherence or relax this time all the way up to almost a second at low temperature. And so this is one of the latest work. And so this is fantastic. 1 second time at 4 Kelvin is really doing fantastic for solid state systems. But what is more impressive for us is if you look at the T1 times. So if you look at the T1 times, they can be even longer. So you can map out the T1. So this is inverse of the T1 that is plotted here as a function of temperature. This fantastic work from the Butker group where they figured out the relaxation processes in diamond. But the point is, again, you have to do this kind of temperature dependent, and then you have to do some kind of fitting to different expected models for spin relaxation. But the key point for us is to look at these numbers. So these are 3 different NV centers with different, or 3 different samples, diamond samples with different doping densities. And at low doping densities, you can really achieve very high relaxation times. In fact, now at 4 Kelvin, the latest one, they have even shown going up to an hour. So an hour for electronic spin, there's not a nuclear spin. Nuclear spins can have longer. But at 4 Kelvin for an electronic spin in solid state, 1 hour is a really fantastic, it may be one of the best that you can hope for. And similarly, there are other works also where they're doing other tricks, and they can reach a T1, as you can see, of a few hundred milliseconds at 77 Kelvin and all of that. So the point is that T1 is long, and T1 is less affected by surface conditions. And T1 does not depend, at least at room temperature, does not depend on doping. T2, on the other hand, is very strongly affected by surface conditions. And this becomes important because normally you want to bring your sensor close to the sample, which means you need to bring the NV defect close to the surface. And so the T2 can become worse. And similarly, it can also depend on the doping. So these are the advantage of why we are doing T1. So I'll just show this last part and I'll wrap up, is how we are using all of this then. So we're going to look at relaxo-based metry for spin relaxation mechanism for doing spectroscopy. And this is just one example of what we are doing is here. We are going to look at, these are basically, this is what we did is we took a diamond, which has a thin layer of NV centers. And this is some base for our experiment. This gives you a variable gap between a ferromagnet, in this case permalloy, from the NV centers. So we grew some spacer layer. There are no microwaves applied. And all we are going to do is the effect of magnetic noise that comes from a ferromagnet on the relaxation rate of the NV centers here. That's what we are going to be monitoring. And so that's what we can do here. This is the protocol. As we said, we initialize the spins using the green laser. Then we wait for some time. And after waiting for some time, we measure the signal. And then, of course, we have to repeat it many, many times over. And so as a function of time, you have seen those previous plot, we can then do an exponential fit, and we can extract the spin lifetime. What is being plotted here is those extracted spin lifetimes, or the relaxation rate, the inverse of the lifetime, as a function of distance and as a function of magnetic field. Because the magnetic noise from the ferromagnet depends on the magnetic field itself. Okay, so that's why we are changing the magnetic field here. And so we could correlate this. Again, in the interest of time, I won't get into too much detail, but the main idea is that you can map out the magnetic noise profile, which is very closely related to its own spectrum, okay? So you can do this, you can mathematically write what is the spectral overlap between the NV resonance, between the NV's resonance and the magnetic noise that is being created by the ferromagnet. And you can do this, you can mathematically model it. But the main idea is pictorially is that there are multiple spin waves in the ferromagnet, and these spin waves are what are creating the magnetic noise. And when these spin waves are resonant with the NV center transitions, that is when you will change the NV spin state. And that is how the NV becomes sensitive to the magnetic state of the, or the magnetic noise from the ferromagnet. And this, of course, depends on if you have spin waves with higher K values, then you're going to be more sensitive to those. And of course, eventually the spin wave spectrum, as you change the magnetic field, it will go above the NV spin, and then you'll probably become insensitive. So you can basically monitor the lifetime of the NV centers, and you can extract the magnetic noise spectrum of the ferromagnet. And that noise spectrum is related to its own energy structure, to its own resonances. And you can do this. In fact, you can then map out the resonance itself by doing an experiment where you drive the spermaloid. So what you do is, you again have this idea that you polarize the spins, you initialize the spins, and then you wait for a certain amount of time, and then you do the readout of the spin state of the NV. Then what you do is you apply resonant microwaves at the FMR frequency. Now, these are not microwaves at the NV frequency, but at the FMR frequency. So you're actively driving the ferromagnet, and this will enhance the fluctuations from that, and you'll see how we do that. The main idea is that you will see a change of the spin lifetime from the NV, of the NV due to the ferromagnet. And using this, you can create, basically you can do spectroscopy. So this is a field frequency map where you see changes of the NV fluorescence far away from its own resonance, okay? This is far away from the own resonance coming purely because of the ferromagnet. And this matches the FMR, the ferromagnetic resonance condition well. So we could do this kind of spectroscopy. Okay, so I think after this, I'll have 2 more slides. I'll rush through the other ones. And in this particular case, I will discuss the mechanism. The mechanism that is happening here is that you have a driven mode of the FMR, which is going to interact with these spin wave magnons, thermal spin wave magnons. And after their scattering, you're going to produce spin waves, incoherent spin waves that are resonant with the NV spin. And these resonant spin waves, incoherent resonant spin waves, are what are causing the change of the NV spin lifetime. And you can use that to do spectroscopy. And I'm just going to give you, I'm not going to go into the details of all the how we did the measurement. Basically, it's monitoring the light intensity sensitively. I'm just going to flash the results here. that see the similar thing as permalloy, but if you do this on jig, you can see this much better. Up here, what you're seeing are the NV's resonances, and it's not nice, sharp, discrete lines because we are using an ensemble of NV centers, and the NVs are nano diamonds, which have NV axis oriented and different orientations. So don't worry about the details of this for now, but this is coming from the NV itself. What is important is that we are able to see the spectrum of the NV. So we are able to use this idea that the magnetic noise from the ferromagnet is relaxing the NV spins by monitoring the changes of NV spin. You can do spectroscopy of the FMR itself, but now we have a tool to do spectroscopy at the nanoscale. That's the key point. You can do this in many other materials, and other people have also done it now. Fantastic work. We had shown it initially, but now there's an excellent work coming from Yakugi group also showing similar ideas. I think in the interest of time, I'm going to stop maybe with this one slide. You can do a similar thing where we have now been able to show paramagnetic spins also. So we can do, in this case, spin waves is not the thing. We are still chasing the exact microscopic mechanism of how it's happening, but we are fairly sure it's related to a paramagnetic spin relaxing the NV spin. And the exact mechanism for relaxation we are trying to figure out. But the main idea is that you can do spectroscopy of paramagnetic spins also using this idea of relaxometry, where you are sensitive not to coherent oscillations of NV because of these spins, but the relaxation of NV due to these spins. And that's what we are doing. That was the last slide. Before I come to my conclusions, I will want to thank all my collaborators at various places. And I apologize for rushing a bit towards the end, but hopefully in the initial part, you got some of the basics. And if you have doubts, I'm happy to answer questions. And this is, I'll leave here my conclusions up on the board for you to read. And yes, I think I'm happy to take your questions. Thank you.
Yeah, thanks, Praveen, for a wonderful talk. You can actually stop presenting, then people can type their questions in the chat box.
Sure, I'll do that.
You can see there is a chat box below.
Let me open the chat window. Okay. Does AM do
there's
something?
One question.
Cascading, are there mathematical models to, okay, so there are many questions here, thank you. So let me go one by one. Does AM do something like a cascading effect? I'm not sure what cascading you're talking here. I may have to listen a bit more, but AM works, it's basically like a diffraction grating. So it basically changes, it's a diffraction grating for the light. So you're tuning the frequency ever so slightly. So you can go into a different mode. So you can turn it. It's a voltage controlled diffraction grating, you can say. And so it's causing the changes to the light, or it can be used to change light intensity. I'm not sure if you're asking cascading because I was going back and forth in that picture, which is a good point. If that is what you're referring to, they did a double pass in that particular system. Because the one thing experimentally, what you have to understand is that if you're going to do this T1 relaxation, let's say, especially for T1, it's important. If you're going to have a T1 which is very long, what you try to do is you initialize the spins and then you want to keep everything very quiet. Nothing should be going. So if your AOM leaks even the tiniest amount of light, it's going to lead to an inaccurate measurement. So it's very important. So normal AOMs can give you what's called the extinction ratio of about 1 to 1,000 normally, maybe 10,000 in the best case. In many times that's not enough. So that's why they were doing the double pass. I'm not sure if that's what you're referring to, but you can ask me later again, and I answered some other question than what you're imagining. The second one is the mathematical models. Yes, there are mathematical models. There are even quantum mechanical models. It's a bit tricky in the sense that we don't always know enough about our system to use the model. There are textbooks also, so I can refer to you to Abraham, which is one of the Bibles for magnetic resonance. There is also Schlichter. There are other textbooks, I'm also sure, but where you can see some of these descriptions. And nowadays, of course, with the quantum computing becoming more and more important, people are also talking about these things. Maybe in a single spin picture, it's a bit more easier. You can control the environment nowadays more. But generally, it's a bit tricky, even if you have a mathematical model, to get quantitative numbers out of it. Most of the times, you have to rely on experiments. But there are models, and we can discuss more in offline if you want. Basically, it's a mathematical coupling, right? So again, you will have to have dipolar coupling of some sort, and you'll have to figure out what is your local environment, how the spins are distributed. So you'll have to make some assumptions about the system. So it becomes a bit tricky. What are the methods to preserve the lifetime other than creating isotropic diamond? Yes. So this is what I was showing. So one of the other ways what I'd shown, I was rushing through it a bit. So one of the latest, so I'd shown that they were growing these NV centers in doped diamonds. So they, contrary to what you would think, that they were actually putting it in N-type diamond. They were putting in phosphorus doped diamond. What they found is that they can be charged state, can be stabilized using that. And many times for NV center, let's say, what happens is the charge state fluctuations, and this is what Tanmay was also talking, how to control the charge state, because charge state fluctuations can also lead to decrease in coherence. And so stabilizing that, and there are people also talking about putting in p-n junctions and all of those kind of things. And so there are other ways. And of course, there's always the Haneko and the dynamic decoupling schemes, which is the most common way of increasing. But from a materials perspective, that's what people have been isotopically pure, and these. And there are also things people have figured out, annealing techniques. So you could have specific annealing techniques that you can do where you can get rid of clusters. So you have vacancy clusters, and you have other spins that can cause issues. So how to get rid of those. So, but these are materials issues that are still being worked out. And this is an active area of research, I would say. Then we have, is diamond sample cost effective? This is a general question. No, diamond sample is not cost effective. Diamond sample has problems also that we in the country don't have. It's hard to get. It takes time. With government regulations in general being what they are today, it's harder. It's harder because there's also import and export restrictions, both in the countries from which we get, both our countries. So you have to be careful, you know, when you get there, more loops, you have to jump through hoops and loops. But once you do get the right sample, you can do some fantastic science. And that's what we spend the money on. So that's the hope, at least. So that's what we're working for.
If you scroll down, there is another question. What
yes,
exactly
so thank you. So I should thank back the person for the compliment. And then what exactly is computer noise in cable? Oh, so computer noise is, so all electronics will have noise. So let's say a very common frequency, if you look at if you hook up your spectrum analyzer, I should check and make sure. So you will see something around 15.75 or something like that, if I remember, 15.5 kilohertz and harmonics of that. So 15.5, 31, 47.5, you'll see little blips. And so these are coming from not just computer, I would say, pretty much any electronics. So most of the electronics, so they will have their own. Oh, sorry, was there somebody?
No, it was just random.
Okay, so you will have noise that all of these, so basically they're electronic components that have their own oscillators, they have their own things happening inside them. And so those will create noises. So computer noise is probably not the best word. I should have said electronics noise. And so you should try to decouple your system from your computer as much. So typically when you want, you need to have other filters in between to try to get rid of such noise. Okay. Anyone else?
Praveen, I have a sort of question, a bit general.
Yes.
For example, in this ITC materials,
yes,
we know that magnetism or magnetic oscillation, these collective modes play a key role. Is it possible to sort of probe it through diamond? That is the effect?
Yes. In fact, this student Anshuman, whose animations I was showing. So part of his, sorry, not Anshuman. So I have Anshuman and I have another master student also who is working. So what they're working, I mean, these are master students with whom I'm working, and even Kasturi also has a paper now, and other people in the US have also done. Yes, so there are different things that you can do. First is, of course, you have the Meissner effect. So people can monitor the TC. So as you're going through TC, you will have the field being expelled. So you could have a change of the field, and so you can monitor this. So this is the simplest. And in fact, the signals can be fairly big because, this change of, we are talking typical sensitivity of NV centers in the nano Tesla range. The change with Meissner fields can be, of the order of few Gauss. So, which can be fairly big. So you can have a fairly big change. The other thing is vortex states. So you can look at vortex states. So understanding the vortex state is another important. So you can look at correlation lens. So all those kind of, and you can do now localized studies, right? So you can obviously do localized studies. So you can look for inhomogeneities, or you could look for specific effects of putting in some impurity or something. So this is a fairly active area of study right now. It's becoming quite important. So then people have also looked at noise also. So people have done, let's say, noise spectroscopy of skyrmions. So you could think of, if you have ideas of right before the transition of magnetic noise, because phase transitions typically will lead to enhanced noise. So you could even think of looking at the noise spectrum of superconductors. So all these kind of things are definitely quite interesting and of interest to us.
I was there was a paper, I think, a couple of years back in Science. They have used this neutron diffraction to check the collective modes. The claim was that there was something like string type of mode. The propagation having a tail kind of thing. That
it's neutron scattering, not diffraction.
Neutron scattering. Yeah.
Scattering, because what happens is this, the Q vector, right? You have the dispersion. So that Q vector is the one which uses, yeah. So you can basically map out the whole dispersion of magnons.
That will be fantastic. The only thing about NV is, I don't know if we are right there in reaching the Fermi surface, how close to the Brillouin zone you can get, because the K vector here, you can bring it closer and closer. But the K vectors, you will have to see what sensitivity. Of course, it's an atomic sensor finally. So in principle, it can be sensitive to fairly high K. But we have to see experimentally how close we can get. So that's something we have to see. And that will be a very interesting thing to try to work on. So, okay.
Yeah, very nice stuff. Really enjoyed.
Yeah, thanks, Praveen. Very nice.
Yeah. Cool. Okay. And I should thank for so many people on a Saturday evening,
and asking questions.
Right? I'm quite impressed to see this.
That is quite amazing. People are asking quite a bit of questions, because I was saying earlier we are not asking. So maybe we'll get some good students now out of this.
So may I ask, what is the composition you think of? I know that you probably don't know all of them.
See, the statistics, what is shown in that google.org, it could be very misleading. See, for some, something like out of 50,000 registered students, so many people are from Sri Lanka, so many people are from here, there.
Okay.
PhD, faculty around 300, post-MSc around 500, like that kind of distribution. But how many are really attending? If you see the names, around 150, 200 are attending from the names. And
and there are a lot of people in that YouTube live. So that you cannot count because they are not in the.
I'm impressed because you have been having this for a month, and it's the fag end of that on a Saturday evening. This many, I have to say, you guys have done a very good job.
Well, in the lockdown, what is Saturday and what is
right? We didn't have any conference, no talks. So it's good, we are just getting updated with all the details. I am not minding so far. So
good. Okay.
Thank you.
All right. Thanks again for everything. Okay.